All right, good morning, everybody. We're going to get started here. It's Friday, so happy Friday. It's the last day of the 2022 ISS. Hope you all have had a good conference this year, and it looks like we're going to wrap things up strong today. So in this morning session, we've got a tutorial, a two-part tutorial, and as well as a talk at the end of the session. So we'll get started with that first tutorial. Our speakers will be Dr. Joe Schoonover and Guy Thorsby. Dr. Joe Schoonover is a scientist and research software engineer at Fluid Numerics, and Guy is a business developer at Fluid Numerics. So Joe, please take it away.
Thanks, Brian. So today we got this tutorial split into two parts. We're going to show you how you can use Google Cloud for continuous benchmarking. There is a hands-on component to this. So some of you have requested accounts for the tutorial, and you should have been able to set those passwords for that. If you haven't done that already, you should just check through your inbox, make sure you have the waterchange.org training account set up. We're going to be going through a code lab that is available online. So if you don't have one of the training accounts, you can do this tutorial at any time. So that's at Fluid Numerics RCC Run Demo on GitHub. And of course, if you don't have the account, certainly following along and with what we got going on today, if you have questions, feel free to unmute yourself and ask them, or you can post those questions to Slido. In case you didn't catch our talk yesterday, I just want to give you a brief overview of what it is we're building today. So this week, there's been a lot of different talks on continuous integration and other practices to automatically test your code. And the way we look at this, and from our perspective, is kind of looking at this process as what we call an image bakery. So it's something that turns your source code into an artifact you can distribute to end users. This could be compiled binaries, Docker images, Singularity images, virtual machine images, however it is you choose to package your code. The meat of this environment is essentially this center column here, where you have a build environment that can create those artifacts. And then you have a layer that's doing some kind of testing on those artifacts before you actually make them available for your end users. So we're going to focus on how to build this middle section out today on an existing repository. So that RCC Run Demo is a very, very simple mock-up of a sort of a template scientific application. We've got some Fortran code in there with a make file. And we're going to basically go through this process to create Docker images. And then I'll show you how you can use RCC Run to do automated benchmarking on top of just the build process. For the build environment, we're going to be using Google Cloud Build. Today, we're going to be focusing on how to create those Docker images and Singularity images. And we're going to create Singularity images, particularly because the testing environment, RCC Run, requires either a Singularity image or a VM image for testing. So like I said, that testing environment is going to be RCC Run, where we'll actually do a lot of the execution. And then at the end of this whole process, you'll be able to see in the test accounts that we've given you in the Google Cloud projects where all those artifacts get posted, so that you can in turn ship those to end users. Again, another recap of some stuff we talked about yesterday to set the stage here, just to familiarize yourself a little bit what needs to happen in that RCC Run workflow. So once we build a Docker or a Singularity image, the RCC Run step has to do a few things for us. In order to do the benchmarking, at least on cloud, it has to create some compute resources on which we're going to execute some jobs, and then we'll collect and report information to a database so you can later analyze performance of your application. And then at the very end, delete all those resources so you don't continue to rack up charges on a cloud environment. Underneath the hood, what's going on the resource creation, RCC Run takes care of building a Slurm controller using what's called Terraform. And that Slurm controller basically allows you to write your tests as if they were Slurm batch jobs. And when the jobs are submitted to the Slurm controller manages creating additional compute nodes to give you access to a variety of compute resources on Google Cloud. So it allows you to start testing your application and how it performs across various CPU platforms and different GPU platforms. Again, just for your awareness, since RCC Run is completely open source and you were interested in digging into some of that code, the way jobs are run is by issuing commands over SSH to that Slurm controller. Essentially, there's templated SBatch calls that leverage some of the instructions that you're going to provide in the repository we're going to work through today to schedule those jobs. In terms of bringing back information and collating the benchmark information, including runtime and the amount of memory used, there's a little bit of stuff that we have to migrate back from the cluster and do that reporting to dump that data up into a service called BigQuery. Once that data is in BigQuery, if we have time today, we'll walk through how to visualize that data using some dashboarding tools called, one of them is called Data Studio. So if we have time at the end of the tutorial, we'll get into how to work with that information. And at the very end, RCC Run will take care of deleting those resources. All right, so a couple tips before we get started. If you do have the waterchange.org training accounts, unless you're familiar with using Chrome identities, we highly recommend starting an incognito or private browsing window, depending on if you're in Chrome or in Firefox. Make sure when we go through the first couple steps here that you are logged into your training account, and definitely ask questions along the way. So, I just don't want to get too far ahead and leave anyone behind. So please, if you're having any trouble, just unmute yourself and ask a question, or you can reach out to Slido. Where we're going to get started today is in this RCC Run demo repository. So let me get rid of this screen here. In that repository, so it has the source code that we're going to be working with. We did start this repository off with a Docker recipe file, so we're not going to have to write that. And that was just really for time saving, but we will cover how that works in case you're not familiar with how the containerization process happens. The code lab that we're working through, if you scroll down into the README, there's a link for a code lab tutorial. If you want to go ahead and open that up, you should see a page that looks something like that. Before we go through the steps in the code lab, I just want to give you a brief overview of what we're starting with in this repository, since this is, basically a new piece of code for you. We have 3 directories here. We have a source directory that has just some simple Fortran code in there. The application that's built here is a simple 5x5 stencil operation. It does some smoothing. It takes in 3 arguments to specify a grid size and then how many iterations we're going to apply to a smoother. So we can play around today when we do the benchmarking with how big we make the problems that we're going to benchmark that way. And then there's a simple makefile to build that application. Now that's in terms of, what you might see in a typical research computing code, you usually have some place where you have all your source code, you have some type of make system. And the way we end up packaging this today is using Docker. So there's a Docker recipe file that it just sets up an environment for us starting from a Debian Linux operating system. We're going to install the compilers, things we need to build our application, and then we'll actually build the application. And where it ends up in the end, inside the container is underneath opt demo bin. In terms of how this gets used during our build process, now, normally if you're working with Docker and you're just manually trying to trigger builds, you would run Docker build and then give it the path to that Docker file. So Docker would, basically create that image for us. We're going to be working with some things that I've provided as a starting point, particularly this cloudbuild.yaml. So the way Google Cloud Build works is you just need to essentially provide a set of instructions that tell Cloud Build how to build the application. Here, we're going to create a Docker image. So I'll break this down here. There's 2 sections right now. There's steps. So these are the actual steps that get run during the build process. Each step is identified by a human readable ID. So this first step here is build Docker image. The name refers to what's called a builder name. Now, a builder in Cloud Build is itself a Docker environment, so that you have some flexibility in how you choose what tools to make available. And this is where it gets kind of weird. So this first builder is a Docker image that has the Docker command installed. for us so that we can actually run Docker build on our Docker file to create this Docker image. Now, after that image is created, we can use this Docker image as part of the next build step, where we're just going to run a simple test to run that application that we've built. So that's where we're starting today. And these are the usual ingredients when you want to get started with cloud build that you'll need to have in your repository. Either a Docker file, or if you're more comfortable with Singularity, you can do a Singularity image file. But we're going to start here. And I think we can go ahead and jump into the code lab. So there's a little bit of business we need to take care of in the beginning. Once you have your training account, or if you're using your own Gmail account or institutional account, we need to get into Cloud Shell and set up your Google Cloud project. So on the first step here, we're going to go ahead and hop into this link here. It's the shell.cloud.google.com. And when you hop into Cloud Shell initially, so I guess I should back up because sometimes I forget, the level of familiarity everyone might have with Google. So Google organizes all of your resources, so compute, network, and storage, into projects. And the projects really are helpful for controlling who has permission to access and view various resources, as well as to organize how you're doing your billing. So if you had say multiple software teams at your organization, you could have a project per team, or you could have a project per application you're working on. But today, we've given in those training accounts a single project per user, so you have your own dedicated project to work on all these activities. So we need to actually set that up when you get into Cloud Shell. So this first group of commands, if you copy those, and once you're in Cloud Shell, you'll have to go through these agree to the terms of service. Don't worry, you're not getting charged for stuff. We've taken care of that part for you. All right, well, got it. And then let me make the text bigger here so everyone can see what's going on. All right, so those first two commands, one, the export command that's pulling that G-Cloud project list, it's going to find the project ID that we've assigned to your account. And then the next command that configs that project is going to make that project visible. So at this point, you should have, of course, your training account up front at Cloud Shell. And then you should see your project ID right there. Again, don't hesitate to reach out if you have any questions. We don't want to leave anyone behind. So we're going to actually be working with two repositories today. The first one is this RCC run demo, of course, because that has all the source code we're going to be working with, and we're going to be modifying the cloud build setup so we can use RCC run for benchmarking. So once you've set your project, we'll go ahead and clone this repository into Cloud Shell. Okay, clear that screen a little bit. The packing of the commands there. So basically we cloned RCC run demo, and now we're underneath that CI directory. And underneath the CI directory, we've provided a Terraform directory. Now Terraform is an application that interprets HCL files. So it's a markdown language that creates resources on Google Cloud. For the benchmarking work, there are a number of services in Google Cloud that we need to use. And when you first get into a project on Google, none of those services are enabled. So we have to enable all of those. And additionally, we wanted to set up a BigQuery table for us to dump all of our benchmarking data into. Now, if you take a look in that TF directory, there's a few files. You have main.tf, io.tf, and then this tf vars. The main.tf is a template that describes what resources to create within any Google Cloud project, but it leaves some variables that can be specified on the fly. The variables that allow you to change, customize something for your specific project are in io.tf. And the TFVars file is where we're going to set the value of those variables. So if you look at what we have in auto TFRs, this is actually a fairly simple setup. The only variable to set is the project. And what we're actually going to create here is we need to enable cloud build so we can use it. We need to enable compute engine, which is the service that provides us access to compute memory, GPUs, disks, all that stuff, networking. We need to enable BigQuery. And then, of course, we'll create that BigQuery table. Now, the main.tf file we have provided for you is something that if you're wanting to adapt this to your own application, you could use this exact directory in your own piece of software to get your project set up. Now you'll see right now we have project is just in these carets here, so we need to actually substitute that for your actual project ID. You can either open this fluid.auto.tf_vars in a text editor and swap that out manually, or you can use that sed command that we've provided in the code lab to do that search and replace for you. So if you take a look at that fluid.auto.tf_vars at this point, that project should be set to the same value that you'll see out in front in Cloud Shell. Okay. So there's a few steps to using Terraform. Terraform needs to interpret these files and tell us what it's going to create first. And then we can decide whether or not we apply the plan. So if you split it up in those two steps, there's I guess I should say there's really three, right? We have a precursor here where we have to initialize Terraform. Terraform's going to look through all of these files, tell us what resources it needs out there in the wild, to figure out how to make the calls to Google Cloud to create those resources. So those first two steps there, the init and validate. Init will figure out what it needs to download in order to make the correct calls to Google, and validate will make sure the plan that we have even has correct syntax. So we'll go ahead and run those first two, init and validate. And you should see it's going to download a couple modules, and you should see at the very bottom, configuration is valid.
There's some credentials that have to go from Google Cloud into Terraform at this point, right? And I know when I run this on my local system, those credentials have to be put into a makefile or something.
Yeah, so if you are doing this on your local system, you'll want to do gcloud init. You'll need to have the gcloud SDK installed, which is why we recommend doing this in the Cloud Shell, because in the Cloud Shell, all those environment variables are set for you. But yeah, if you're doing this on a local system, you'll need to run gcloud init and then log in with that waterchange.org account. Unless, of course, if you're doing this with your own account, you should, it's either you can set the Google application, let me see, it's yeah, Google application, or no, is it Google default credentials? I actually can't remember off the top of my head. I think the quick way to do it is gcloud auth login, and that will create a credentials file and set the appropriate environment variables for you if you're doing this locally. Again, for the tutorial today, I highly recommend you use those water change accounts if you got them. I hope that answers your question.
Yeah, I just wanted to get a little bit more detail on the process of connecting your local setup to your cloud account and its project, as well as the region and the credentials that have to be put in there. And it seems like a lot if you're coming at cloud for the first time, but when you're used to the fact that you pretty much always package together, here's my project and here's my region and here's my login, and those all go as a unit for each project, then it makes more sense.
Yeah, no. So like, the deal today was try to set up something to where we could focus on how to use cloud build and leave some of these other details. Like, is normally to get started on cloud too, you need to, put down a credit card and all this other bits to really get going to make that jump. But yeah, if you are doing this locally on your own system, you need to have the gcloud SDK, and you'll want to do gcloud init and log in with whatever account you're going to use. And it really ends up being those two steps once you set up billing.
Okay, thanks.
Yeah. So the next thing we're going to do is create a Terraform plan. And this work we're doing here in this first step is something you'll do one time to set up your project. And you'll likely never think about it again until you go to tear down the project when you're trying to clean up everything. All right, so here we've got, you should have a plan, which is going to tell us all the resources it's going to create. You can see it's going to create a service account, which if you're not familiar, service account is essentially, you can think of it like a bot that's going to do actions on your behalf. So we're creating a service account for RCC run. We're going to enable project services. So we're going to enable IAM. What else here? We got container registry, which is where we're going to post those Docker containers. Of course, we're going to enable compute because we need that today, and cloud build. And BigQuery. Higher up, we've got some IAM roles we're going to apply. So we're going to give the cloud build service account fairly open permissions. Now, this is a tunable parameter in the Terraform file we've given, but just to make things easy for this tutorial, we're giving it pretty wide open permissions to basically control compute and BigQuery resources. So that's what those IAM permissions are there. So that's kind of the gist of it, right? We're going to create a network here to deploy our cluster to during benchmarking. So all this stuff is coded for you. And the modules, again, are all open source so that you can reuse them at your convenience. A lot of what we try to do is take a lot of the pain out of figuring out all this stuff just by consolidating a lot of what we're going to do and how you need to set up your projects to get these activities done. All right, so now we've created a plan. You can see at the bottom, they give you a command that you can run to make those changes to the project. So we're going to go ahead and run that Terraform apply TF plan. It's going to take a couple minutes to enable everything. So we'll let that go. One note, I've noticed when we went through testing on the code lab this week, sometimes it happened and sometimes it didn't, but we're going to go ahead and run these next set of commands anyways once this apply is done. There's two service accounts that we're really going to work with today. One is this RCC run service account that we're creating with Terraform. When you enable the compute engine API, there is a service account that comes with that. And in order for things to work, that service account needs to be active. And we found an odd thing that sometimes that service account, although it was created during this process, it was never activated. And so these next two commands here are going to do that for us. So the first one here is going to find that compute engine service account and assign it to an environment variable called service account. And then we're just going to run that gcloud command to enable it. So once this is done, we'll get that taken care of. If there are any questions, please reach out. Make sure you're not getting too far behind. Okay. So at this point, you should have all those resources added. We're going to go ahead and run those next two commands to create that service account. Now, if you are interested to see, one of the resources we created that we're going to come back to a couple times today is that BigQuery table. So in that code lab, I did provide a link to get over to BigQuery pretty quickly. And the first time you go to it, you should end up having to agree to some terms of services again for your account. Okay, so just hit I agree and continue. And then up at the top where it says select a project right next to the Google Cloud Platform logo, it's up here. If you hit select project, up and select from, you'll change that organization to waterchange.org. And then you'll select your project from that list. So again, to get there, you'll go to select a project, change the organization to waterchange.org, and then hit that water change project that you have. Okay, we'll go ahead and hit done. We don't need to have the tool tips because we'll be walking you through a lot of this today. Now in the BigQuery page, there's a few things that we'll go through here. On the left side, you'll have all the projects that have BigQuery data sets. So you can think of BigQuery like a more robust version of Google Sheets. It's just rows and columns of data, but it can scale pretty large. Underneath our project, we have the RCC run table or data set that was created, and that RCC run data set should have a single table called app runs. And you can see the entire schema should give you an idea of all the things that get collected or that can get collected during a benchmark run with RCC run. So you think we got things like allocated CPUs, GPUs. There's a lot of optional fields, so not all of these are always used. You get batch options. We got options to specify what kind of file system your application was run on. So we got details for Lustre and other types of file systems in case your application is file IO sensitive. This kind of stuff is important to track. The compiler you use, target architecture, GPU type and count, the number of nodes, exit codes, standard out error, the Slurm partition, which we'll talk about why that's important here in a little bit, runtime, and then that max memory. So you can see we're setting up an environment that allows us to really track how our application was run to give us a specific runtime or amount of memory used. To some degree, understanding how that changes as you change the application, as you change build flags, compiler, can really help you make good decisions about where to recommend doing deployments or where you might spend some time trying to improve performance on your application. All right, so that's step one there. We're going to go on to some more exciting stuff here. We're actually going to trigger our first build, and we're just going to build this what's included in the RCC run demo repository. So all we're going to do in this build is create the Docker image, and we're going to run a simple test within the cloud build environment. Now, the project ID you might see inside of here, cloud build provides a lot of built-in substitution variables for us. Project ID is one of them. Cloud build will know what your project ID is, and if you ever wanted to use that or any of the other substitution variables, you can reference them inside of that build YAML. So we already went over what's inside that Docker file. So let's go ahead and talk about how to kick off a build. So let's go to the root directory of that RCC run demo repo. And this next command here is we're going to manually trigger the build using the gcloud SDK. So you'll run gcloud build submit dot, and then we'll pass it a config file. Now I'm not going to do what I want to show you here is what the build logs look like directly in standard out. Let's see, I think I saw a few comments come in the chat here. Okay, I think we're good. What's going to happen here when we run this command from the root directory of the repo is cloud build is going to tar up your whole source code repository and migrate it into an isolated environment where it's going to run those two steps to do the Docker build, and then it's going to do a Docker run on that image. And for a lot of applications where you might not need GPUs, you don't need the scale very big, this is a really easy way just to do very, very simple serial, or if you're doing a couple MPI ranks, etc. You can do all this within the cloud build environment. So for simple tests, lightweight tests, this is a good route to go. The reason RCC run was developed is because we had a need to test applications at scale, so on clusters, and we have applications that require GPUs. And if we're not able, like GitHub Actions and even the Google Cloud Build environment itself doesn't provide access to clusters. It doesn't provide access to GPUs, which is why we ended up needing to create RCC run to do things on a broader set of resources. So in this process, you could see the output. You have which build step it's running, that ID that you assign to that build step, and then it'll give you any of the standard out, standard error messages that come out. So you can see we got step 0, step 1, we're doing our test, and it ran. And now what it's doing is pushing that. Since both of those steps passed, it's going to push this to container registry. So to help you kind of see where this information gets relayed, because it's not just coming out to the terminal, it actually gets saved long-term. So you can have those build logs well after the fact. If you're back in your Google Cloud console, up on the top left, there's a navigation menu. It's those triple bars on the left side of Google Cloud Platform. So top left, hit that navigation menu. The easy way to look around is hit that view all products and scroll down until you get to, actually I have the nice search on the side there, CI/CD. And you'll see there's our container registry, which is where our container is at. And then we got cloud build. So let's take a look at cloud build first. Now, if you missed where I went there, in the code lab, I did provide those links to the container registry and the cloud build dashboard. So in that cloud build dashboard, let's go ahead and hide that tooltip there. We've got that one build that we just submitted. It told us where it came from. So when it says Google Cloud Storage, this is really that tarball I was telling you about. That source directory was tarred up and shipped up to cloud storage, really, which then relayed it to cloud build. If you click on that build, you could see, again, those two steps that were run. So we got the build, where it actually created the Docker image. And then we got the test, where it just ran our application inside that container. At any time, if you wanted to come back to these build logs, they will always be here until you delete the project or you delete the bucket associated with cloud build. So you do get that ability to dive back into a previous build. So let's go ahead and pull up container registry. So again, we'll hit that navigation menu in the top left, view all products. On the left side, you see CI/CD. Then we're going to go into container registry. You see now we've got, right now we've only got one container in there. It's that smoother container for our application. If you click through on that, you'll be able to see all the different versions of smoother. So as we go through today, we're going to do multiple builds. So you'll start to see these stack up over time. And right now we're just doing really simple tagging. We're just going to tag everything as latest. So every time I do a new build and I retag it as latest, that's going to migrate up to the latest Docker image. Okay. So this is where, again, it can be kind of weird at first if you're not used to working with containers and with cloud build. I remember this being a little weird for me when I was first learning this, but each step in cloud build itself is a Docker container. RCC run, because of that, is packaged in a Docker container to provide you access to this command line interface we've created to handle benchmarking for you. So before we actually add the RCC run step to our build process, we have to create the RCC run Docker image. So we're going to clone the RCC run repository, which has all the source code for handling the automated benchmarking. And we're going to create the Docker image so that we can use it inside of cloud build. So we're on step 4 here in the code lab. Sub step 1, we're going to go ahead and clone RCC run. So you'll need to go into your Cloud Shell, get to that root directory, and go ahead and clone RCC run. And then you'll need to navigate into that RCC run directory, and we're going to use cloud build, surprise, to build that Docker image for us. This command, I did it on purpose this way to introduce you to another command line option called substitutions for cloud build. Once this is done, I'll show you what happens in there, but essentially you can create your own substitution variables in cloud build. So if you had, for example, if you wanted to have a build setup that could toggle between compilers, it could change, the tag you're going to apply to your resulting container image. For example, for us, we have Docker images for the Spectra element library in Fortran. We have Docker images for AMD GPUs and NVIDIA GPUs. And so we use that to templatize some of our builds. So we can basically use one set of source code for doing the build process, but swap out, what the target architecture is through a build variable. Now here we're just using the substitution to set a tag on that image. But just know that that's there and you can use that. All right, so if I look back in the container registry, now that that build is done, you see we have two containers. We have Smoother, which is our application. And now we have RCC run, which we can actually now leverage since it's containerized as a build step in Cloud Build. One more precursor before using RCC run. The reason why we've included this step is we've seen some groups that definitely prefer to use Docker images for their build process. Unfortunately, to use RCC run, we only support Singularity and VM images. Now, the easy thing here, the nice thing, well, I guess I should say the nice thing here with Singularity is you can convert a Docker image to a Singularity image without a problem. But to do this as part of the build process, again, we need a Docker image that gives us access to the Singularity command. There are public images, so we're actually going to pull this one from key.io, key.io Singularity, only because I've tested up to 3.7.1 in this tutorial. That's the version we're going to use. So we need to modify in the RCC run demo repository the Cloud Build YAML to add a step to convert that Docker image to a Singularity image. Because once we have that Singularity image, we can pass that off to RCC run so that it can run on a Slurm cluster. So in your Cloud Shell, go ahead and head back to RCC run demo. You're going to open up that cloudbuild.yaml. And after that test step, so we'll leave that test step in there. We'll say we're going to build the image. We'll do our lightweight test. And if those two pass, then we'll go ahead and run that the step to convert to a Singularity image. So if you want, you can copy that block in step 2 here and paste it down below. So again, the ID here is the human readable name. We're going to convert to a Singularity image. The name is the path to a Docker container that we can use to give us access to the Singularity command. And the args are what the arguments we want to pass to Singularity. So here we'll do Singularity build. We're going to build a Singularity image file called smoother.sif. And then we're going to pull from the local Docker daemon in the Cloud Build environment our smoother Docker image so that we can convert that to smoother.sif. Once we're done there, oh, come on, give me access. There we are. Thought my escape key broke again. Once we're there, let's go ahead and just test things out to make sure as we incrementally add these steps that everything's still working. So we'll save that file and then we'll rerun Cloud Build. But this time I'm going to add this async flag at the very end. This will basically, once the local directory has been tarred up and shipped up to the Cloud Build environment, we'll be able to interact with the terminal again. And we can instead track the logs from that Cloud Build dashboard. So to get back to that dashboard, go to the navigation menu, view all products, CI/CD, and Cloud Build. And there you can see that build is currently running. Okay, so this was our first one we did down here. This is the one to build RCC run. And then this build is the one we're currently doing. And you can see now we've got 3 steps. We got build the Docker image, gonna test it, and then we'll convert to Singularity. So we're gonna let that run in the background while we move on to the next step. Are there any questions so far? How are you guys doing? So this is where it starts to get hairy, learning a new tool.
Navigating the menu in the Google Cloud platform is definitely a little slower for me than it is for you.
Understood. I'll make sure I slow down a little bit. Are you having trouble finding any of the tools so far, like that we've gone through?
I did eventually find them.
Okay. Sorry about that. I'll be sure to slow down a little bit. All right. So we're going to do, we're now at a point where the cloud build YAML is set up to add that RCC run build step. And remember, the RCC run build step, it's going to do a lot of stuff for us. It's going to create a Slurm controller. It's going to migrate the cloud build working directories up to that cluster and preserve the directory tree you have in your repository. So, and then from there, it's going to schedule sbatch commands to run benchmarks. So we have to define some batch scripts to run the test. And we have to define a dictionary that tells RCC run which scripts in our repository do you want me to submit to Slurm sbatch. So at the top of the step 6 in the code lab, I'm describing what up here, what we have as environment variables that you can use when writing those batch scripts. The workspace in cloud build. So when you're in that cloud build environment, everything gets copied to a directory. It's a / workspace. So root workspace, and then it's basically got your source, your application's repository underneath that. Now on the cluster, everything is done inside of a service account home directory. And so there's some mismatches in like the root level directory between cloud build and in the cluster, but RCC run is set up. So if you reference this workspace environment variable in the cloud build environment, it'll be / workspace. If you reference it on the cluster, it will get that path, the full path correct. So this can be helpful if you have some tests that require you to kind of migrate between different directories as your application's running. So I'll show you how to use that one today. And the other one that we'll talk about how to use is this singularity image. One of the arguments into RCC run is going to be that singularity image that we just created in the previous step. And you can reference the full path to that on the cluster through that singularity image environment variable. So we're going to start by creating these 2 ingredients. The first one being a batch script to run our application. So that's what's shown down here. You'll need to go into that RCC run demo in the Cloud Shell. And under the CI directory, we're going to create a file called singularityexec.sh and add these contents to it. And once we do that, I'll walk you through what we got going on there. So again, make sure you're in that RCC run demo directory. We'll open up CI and do singularity exec.sh. Okay. So this is just a simple batch script. We're going to just change directories into workspace. Now, this is not required, as it'll like automatically RCC run's going to be in the working directory it's supposed to be in when it runs sbatch. Just wanted to surface this command so you know how you could see how this would get referenced, but you again treat it like any environment variable that you might already have. The other thing, you can use any of the Slurm environment variables that Slurm provides. So, you know, the number of nodes, number of tasks, etc. You can also reference any Slurm environment variable in your batch scripts. Here we're just running a serial application, so there's not really any need to do that. Now the host operating system on the cluster provides for you singularity out of the box, and the default image we provide has OpenMPI 4.0.5. So if you do want to use RCC run for applications that leverage different MPI flavors, you'll need to basically, I'd say just reach out to us and we can point you in the right direction in terms of creating a host image that has the matching MPI flavor. And the CUDA installation is by default 11.2. These are all important things to point out because when you run things in Singularity containers, you do need to make sure there's consistency between what you have in your container environment and what you have on that host operating system. Now, all this stuff is documented on the RCC run documentation. So if you ever just need to look that information up, that's up there on our read the docs. So what this command is going to do for us, it's going to run Singularity exec, again, because Singularity is installed for us on this host operating system. And we're going to use that Singularity image environment variable to fill in for the full paths to that singularity image that we just created. Inside of that container, we're going to run the smoother command with these arguments. And again, remember, this is just a 2D stencil smoother. This is just saying to this specific code, we're going to do a 1,000 by 1,000 grid with 100 iterations on that smoother. Okay, so we have our example batch script for running our test. Of course, we're kind of just repeating what we already did, but if for some reason you wanted to make this bigger, if you wanted to go 10,000 by 10,000, by all means, feel free to play with those variables there. Just keep in mind that the bigger you make the problem, the longer the build's going to take. So now that we have the batch script, so the script that we're going to send to Slurm's SBatch, we need to add what's called the RCC run configuration file. So this is the dictionary that's going to tell RCC run what batch scripts to submit into what Slurm partitions those should run under. There's, for each test that gets run, there's 5 variables that get set. One's called the command group. We have execution command, output directory, partition, and batch options. So the command group, much like the ID in Cloud Build, it's a human readable name to group a set of commands. This variable exists, it serves a couple purposes, of course, not just for sorting data in your BigQuery data set, since that command group does get aligned with the benchmark run. If you put multiple execution commands within the same command group, those commands are going to get run in sequence. So we'll automatically insert Slurm job dependencies. This for us, we added this feature when we were doing benchmarks for Wharf, where we had a stage to create the initial conditions and boundary conditions, and then a stage to actually run, like CONUS 2.5 benchmark. And we kept them in the same command group again, so we can get that sequence to occur. But I can also separate out, when I'm analyzing the benchmark data, the amount of time spent, of course, in the input deck creation and the amount of time actually doing the simulation. So you could, just keep that in mind. Of course, yes, it is a human readable name, so it does help with sorting out things in the database. But if you keep things in the same command group, you're going to get those commands run in sequence in the order in which they appear in the configuration file. The execution command is going to be the path relative to the root directory of your repository to the batch script that you want to send to SBatch for benchmarking. Output directory is the specific location, again, relative to the root directory of your repo, where you want to have, if your code generates output, where that output's going to go. And this can be helpful where, if you want to do testing across architectures, you can sort the output accordingly, and then do correctness checks on your model output as a follow-up step in Cloud Build. The partition. So by default, RCC run is going to give you access to a single Slurm partition. And we're using, in this case, partitions to group the various machine types that are available on Google Cloud. And by default, RCC run only gives you a single partition with what are called C2 standard 8 compute nodes. So the C2 is a machine family. And on Google Cloud, the C2 machine family gives you access to Intel Cascade Lakes, with the the guest operating system having a one-to-one mapping to the host system, so to bare metal on Google systems, so that you can preserve NUMA regions. So any of the systems on Google Cloud that start with a C, they're what they refer to as compute optimized. And that compute optimization really just means that if you look at a CPU ID by running like LSCPU, whatever shows up in the VM is going to match what's actually on the underlying hardware. So it does help with performance quite a bit. We're going to start just by doing a benchmark on the C2 standard 8. So the 8 there meaning we're going to get 8 virtual CPUs. A vCPU, for reference, is a think of it like a hyperthread. So 2 vCPUs gives you a physical core. So we'll, in our first test, just focus on that partition. And then you can set any batch options here. So you have really 2 spots where you can set batch options. You can put it in the Singularity exec file, or whatever your batch script file name is, or you can pass them in the batch options here. Now, the benefit of adding the batch options here is that they show up in the benchmarking database when they're posted in the config file, so that you can see how the batch options that you supply can impact the performance that you have. So whether you run with like exclusively on a node, whether you take over a whole node versus a partial node, those kinds of ways of deploying the application through Slurm. If you set that there, you have the ability to do some kind of comparison if that's a degree of freedom you're interested in exploring. So these are the options we need to set in our config file. So we're going to open up a new file under that CI directory called rccrun.yaml. Doesn't have to be that name, but this is just commonly, actually, this is our default name for the file. So unless you have a good reason to change it out, maybe you have multiple configurations in your repo, you could name it whatever you want. But here we'll do CI rcc run, and we're going to paste this set in here. So the command group, we're going to call it smoother C2. I guess the idea here was to name the command group after the application and the partition I'm running on. We'll give it the path to that Singularity exec file, again, relative to the root directory of the repository. So here's CI singularity exec.sh. I'm going to keep the output directory to be the same name as the command group. Oftentimes this is actually useful, especially if you're trying to test out a complete pipeline of multiple things that are running, like I said, like input deck generation and then simulation running. We're going to set the partition to that C2 standard 8 partition. So again, Intel Cascade Lakes with 8 vCPUs. And then we're going to give it these Slurm batch options. So we're going to say, I want a full node. I want to set a wall clock limit for 10 minutes. And I want exclusive access to that node. So I don't want, in the event that you have multiple tests in here, I don't want Slurm to pack other benchmark runs on that same node. So you can get a nice clean measurement of that runtime. Now the timeout limit is actually quite convenient because RCC run, if it sees in the Slurm database at the end that a job timed out, that exiting information gets relayed back to cloud build. And if your application times out, you'll actually fail the cloud build as well. So that's kind of helpful if you know that your job shouldn't run more than a certain amount of time to set that timeout information for Slurm. All right, so let's go ahead and paste that in, and then I'll take a break for questions, and then we can take our 20-minute break after that, and we'll pick up on the next few steps. But let's go ahead and finish this up. So we're going to go into the CI directory and open up rccrun.yaml, a new file, and paste that test in there. And go ahead and save that file. And I will stop here for any questions and discussion for a few minutes, and then we'll take that break at 10 o'clock, and we'll pick up on adding that RCC run build step. So if you have questions, you can unmute yourself or post them in Slido. We'll be happy to address those.
Does singularity exec.sh have to be executable permission?
It does not. It does not. So the singularity command itself needs to be executable, but singularity exec.sh does not need to be.
And from the connection between those last two scripts, it seems that the singularity exec.sh will be run inside of a Slurm job.
That's exactly right. Yeah. And that's currently like the reason why, so one, the VM image option allows you to swap out the virtual machine image used on that Slurm controller. And we've like, if you wanted to create your own image up there that had like Charlie Cloud or Shifter or something else, another container environment, you can do that. There are minimum requirements for that Slurm controller image that we have on our documentation. And we actually have a public repo. It's called RCC apps that has all the build instructions for creating those images. So there's a lot of opportunity to customize that environment where all this goes. But yeah, the default image we have only has Singularity installed for the container environment, which is why out of the box, we recommend using that Singularity image. But yeah, you're right. The command on the cluster that'll happen is basically we're going to do a Singularity exec on that Singularity image we create in Cloud Build.
I guess my question on the connection with Slurm had to do a little bit with how is multiprocessing going to work, or if you're trying to run something with MPI.
So we do have OpenMPI 405 on the cluster. So if we were to do MPI, what you could do is, so in that Singularity exec, and this is what I often do, is I'll do MPI run np slurm and tasks. Oops, not slum. Okay. And then if you had like specific binding flags that you wanted to set, this is why I provide, so there's another file that you can add, an environment file, that, if you had a way to like set certain environment variables in your build process, you can customize the array of environment variables that are exposed on the cluster. And so what I often do is I'll add an environment file that has like mapping options. So like if I wanted to have a bind to core, map by socket, something like that, what I would often do is have these binding options set as a build substitution, and then have those go into this environment file option for RCC run, so that you could just do something like, I don't know, bind options as well. And that information in the environment file gets relayed up to that BigQuery environment as well. So you can also compare how changing different, your own custom environment variables will impact performance. So in terms of like running, with like Singularity underneath MPI, this is what you would do. Now the deal is, when you build your application in the Docker container, if you're using the default image, you have to make sure you're using a compatible version of MPI, ideally matching the same distribution and version. Which again is why, like, where we're at with this is what we really ought to have is a library of these like host images for the Slurm controller that give you options for like whether you want mpitch, OpenMPI, and vapitch with various versions. But maintaining a lot of those images, it certainly costs us money. So we opted to just like say, what, we're going to put this out in the open source world and show you guys how so one, first, of course, help people get familiar with how to do this process. But then, show you how you can also customize those host operating systems so you can have that consistent testing environment. The other reason we went with Slurm is we have an ability to do what's called federation. So if you actually stand up a permanent controller on Google Cloud, you can federate this to your on-prem systems. And you could also schedule jobs through Cloud Build that would also burst onto on-prem. This is kind of beneficial if you're looking to go, from on-prem to cloud to take some pressure off of the on-premise systems, or if you're, if Google doesn't have all the target hardware you want to run on. For example, they don't have AMD GPUs. So, that there are still some limitations, but I know that is a long-winded tangential answer to your question, but I hope I got it in there somewhere.
Yeah, that's a lot of good information, and we like Slurm.
Very cool. Yeah, no, it's like, it's why fix what's not broken, So we're trying to figure out ways to merge like this whole way of thinking about operating in the cloud with what we already do. So I suppose we should take that 20-minute break and pick back up at 10:20, where we'll finish out these last two steps here, and we'll start looking at some data in Data Studio if we have some time.
Thank you, Joe. Yeah, we'll resume in 20 minutes. I imagine if anybody has any questions that come up during those 20 minutes and you want to type them into the Slido, we could address those at the beginning of the next half.
Absolutely.
All right, see you soon. All right, great. I think we'll get going again with the second part of the GCP tutorial here, and turn it over to you, Joe. I don't see any questions in the Slido from the break, but maybe I'll start us off with a quick one. I know you talked about, obviously the intention here is to spin up a cluster for running workflows. You had talked about GPU support. Is there any hardware support or software support for things like GPU Direct or any of those GPU to GPU features?
Yeah, so there's on the, I guess if you think about like virtual hardware side, you have the ability to add up to 8 GPUs per node for the K80, P100, P4, T4, V100 series. And the OpenMPI install that we have has GPU Direct enabled with the CUDA 11 install. On the V100 nodes, particularly if you use the 8 by V100 nodes, those have NVLink between the GPUs. If you do like 4 of the V100s or less, because of the virtualization layer, you still have NVLink, but you're not going to get the full performance out of it. There's also A100 instances, and those also have that NVLink between the GPUs, so long as you're using the 8 by, and they even have a variety for the 16 by GPUs. In our experience, like on the A100s, you got to be careful about like the time of day in the data center region that you're submitting those jobs to, because those are pretty popular right now. Yeah.
Understandable. Oh, thank you.
Yep. Yeah. If there's any other questions, feel free to drop those questions in Slido, or unmute yourself and ask them. Otherwise, I'll go ahead and do a recap of where we're at so far. What we've done is we have a repository that has some Fortran code. We have a make system in there, and there is a cloud build pipeline, that cloud build.yaml, that came with the steps to create a Docker image and test it locally in cloud build. We've prepped a few things here to get ready for our RCC run, which is the bit that's going to allow us to run on more robust resources. So we've got a script, a batch script that we can that will essentially get handed off to Slurm's SBatch to run Singularity exec on a Singularity image that we're building now as part of the build process. We've created a dictionary with just a single test in there to tell RCC run how to submit that test, where to submit it to, and what batch options to apply. So what we need to do now, now that we've actually got the RCC run build step in our project, is to just add that call to the cloud build pipeline. So I did provide some reference for some of the arguments we're going to be using. Now there is a ton of arguments for RCC run, just because we tried to cater this tool to a variety of use cases. And a lot of the options do depend on how much information you want to align with your benchmark. So for example, if you wanted to align the compiler and the compiler version, as well as the flags you use to build your application with the actual benchmark, you have to pass those through as a command line option to RCC run. It doesn't go through your binary and try to auto detect that information. Now, if you did want to take a look at that RCC run command line interface, that link at the top of that 7th page for the code lab will bring you to our read the docs, and you can take a look at all the command line arguments there and some of the default options that are available. We're going to start real simple. All we're going to do is align the two key things we have to align are a get SHA, so the version of the code, and a build ID. So the build ID is a variable that is included with Cloud Build that tells us it's a unique identifier for that specific build of the application. So you have in the database, you'll have two identifiers that you can use to tie to a specific version of your code and perhaps a specific build. The reason why we have these options is, in our case with Self, and we've seen it with others, especially those who are thinking about portability, performance portability. We'll have a single get SHA if you make a commit to the repository, but we'll trigger 3, 4, 5 different builds, all with different compiler flags, different target architectures. And so we'll have multiple build IDs associated with a single version of the code. And in terms of doing some analysis later on the data, it's helpful to have those two columns to sort of pivot off of. Other arguments that we're going to use here is the CI file. So that'll be the path to our RCC run.yaml that we just created. You do need to set the artifact type. Now, built into RCC run, we support VM image and singularity. I talked a little bit yesterday about how the VM image ends up getting used, but today we're focusing on singularity. So we'll set that. And then for the singularity image, we'll need to set the that flag option to the path to that singularity image file that we create in Cloud Build. Now, under the hood, RCC run is going to digest a Terraform TF vars file. So it's a concretization of this Slurm cluster and deploy it for us. And it needs to know, among many other things, the project ID. So we're actually going to use that environment variable built into Cloud Build to fill that in so that it can deploy the cluster in the same Google project that we're running Cloud Build in. Right, and the last argument here is just a Boolean flag. If you don't enable this Boolean flag, what happens is RCC run will surface the benchmarking data in the Cloud Build logs, but it won't post it to BigQuery. This option was included because we had some users who were not interested in running a BigQuery database and instead preferred to parse out the information from a build log. So by default, RCC run does not push to a BigQuery table. Now, our preference and our recommendation is to use a BigQuery table because it gives you a nice already parsed out log of information. So we're going to add that save results flag today. So what we need to do is hop back into that Cloud Shell and make sure you're still connected. Up top, you may, depending on your browser, it may show that the Cloud Shell is disconnected. If it is, just open up a new tab and you should be good to go. So I'm in the RCC run demo root directory for that repository. We're going to open up under CI cloudbuild.yaml. So remember what we have here. We have that Docker image build step. We run the test locally in the Cloud Build environment. Provided those two tests pass, we're going to create that singularity image, which is again called smoother.sif. And after that step, but before that images line, is where we're going to insert this fourth step for calling RCC run. So again, I'll go line by line through what we just added here. So the ID, the human readable name for the step, we'll call it RCC run. Of course, you can set that to whatever you like. If you want to call it benchmarking, what have you, you can do that. Now, the Docker image that we're going to use that hosts RCC run is the one we built a few pages back in the code lab. So we're going to reference gcr.io, which is the Google container registry, where our RCC run image is posted. We're going to use that project ID substitution variable since each of us now has our own copy of the RCC run Docker image in our Google project. And then we'll go ahead and just use that latest tag. So we will always reference the most recent version of RCC run in our project. Now the arguments, again, we're going to supply build ID, get SHA. This commit SHA is, again, another built-in environment variable with Cloud Build. If you're doing a triggered build, this commit SHA is auto-populated. Now in the manually submitted build today, that's going to come back as null or just an empty string. But in the eventuality that we set up build triggers, we'll have that version tracking through that flag. Again, the project ID, so we know, so RCC run knows which project to deploy the cluster to. Set that artifact type to singularity. We're going to use smoother.sif for that singularity image, since in the previous step, that's what we called it. The CI file is that rcc run.yaml that we created in the last page, and then we'll save those results. So once you have that, go ahead and save that file, and you can exit the editor. Actually, if you exit it, go ahead and open the editor back up. So I forgot about this part. The default timeout in Cloud Build is 10 minutes. Now with these kinds of processes, we're adding a controller. So there's going to be time spent to provision that compute resource and the compute nodes. We have to migrate the Cloud Build workspace up to the cluster, of course, then submit the job, run the job, and then pull that information all back down, including any output. And for this specific code lab, and this very, very simple application, this can take anywhere from like 9 to 12 minutes. So in some cases, it may time out if we use the default time limit. So we're going to add an override in the cloudbuild.yaml to reset what we want the timeout limit to be. Now, where you put this is up to you. You can put it at the very top. I prefer to do these kinds of options at the bottom. We're going to add timeout is 900 seconds, so 15 minutes, just so that Cloud Build doesn't fail the build because we've passed 10 minutes of runtime. Now, the actual execution of the smoother run is like 14 seconds, but like I said, the other bits of overhead here is the time it takes to spin up the cluster and move data between Cloud Build and the cluster, back and forth. So we do just need to adjust that a little bit. Now, with Cloud Build, I believe it's once a month, you get 300 build minutes for free. Keep that in mind. And then there is a free tier on the compute engine side. So as long as you keep resources down pretty low, you can take advantage of that free tier. But of course, with high performance computing, research computing, eventually you do have to, pay for what you use, because we as researchers use quite a bit of compute resources. Now, this being said, this whole process, when we were doing this manually, would be a full day's work trying to do all these benchmarks, if not months of kind of manually going through these processes. And this definitely takes out a lot of the headache of provisioning resource, get your scripts together. And, if you're thinking about running across compilers, target architectures, compiler flags, you could easily have, 100, 200 simulations you need to run to get, a full view of how the application's running. Where here, we're reducing it down to just writing a couple dictionaries. All right, so what we're going to do is go ahead and submit this run, and we're going to use that async flag because, again, it's going to take some time, and we do want the command line to come back to us so we can move on to the next step while this is running in the background. So, right, so on page 7 of the code lab, step 5, go ahead and copy that gcloud build submit, or you can pull up the last one you did. Make sure you have that async flag at the very end. Once that's running, if you pull up in the console, so if you're not on the build page, how you can get to that is, again, that navigation menu in the top left. It's the triple bar menu. When you click on that, you can hit view all products. Down on the left side, CI/CD, and then there's your Cloud Build. Okay, so you can see our build is currently running. If you click through on that build ID, you can see now we've got that third step or that fourth step there, zero-based indexing. I'm going to build the Docker image. It's going to test. It's going to convert to a Singularity image, and it's going to pass that off to RCC run. So we're going to let that go. And we'll start talking about the next step here. Because like I said, what we're doing now is testing on the default partition, which is that C2 standard 8. And I know that, a big point of this is to get you access to other resources, things that are bigger than, 8 vCPU, something that has GPUs, et cetera. So I'm going to show you how you can customize the cluster so that you can control those options. So there's one more ingredient we need to add to our repository, and it is a Terraform TF-vars file that has all the variables that control the characteristics of that cluster, that Slurm controller, and the compute nodes that are available that we have access to. Now, RCC run, that repository comes with a default TF-vars file. And since in this case, we've cloned in our Cloud Shell, both RCC run and RCC run demo, we can go ahead and copy that default TF-vars from RCC run and bring it into our applications repository. And then we can use a RCC run flag to override that default TF-vars file so we can, get these customizations for our benchmarking. So that first command here in page 8, the code lab, you can copy it, but essentially what we're doing is copying that default TF-vars file into the RCC run demo repo and placing it underneath the CI subdirectory. So if I'm in RCC run demo, underneath CI, you should have a few files now. You have that cloud build pipeline. That guy, I'm not sure what that's for. That was a mistake in the repo. You should have, but he should be there if you're following along. And we have rcc.auto.tfrs, which is the file we just created. We've got rccrun.yaml, and then we've got our singularity exec.sh. Now we can point RCC run to use that new TF-vars file by adding the RCC TF-vars flag to that build step. So underneath the RCC run args, we're just going to add this RCC run TF-vars flags. We'll copy that out. We'll open up that CI cloud build file. Order really doesn't matter. So if you wanted to put it just at the end, that's fine. And we'll just drop that right in. And so this will tell RCC run to use this file that we've just added to the repository to define the cluster.
At this point, I have a question about the relationship between RCC run and RCC run demo. As I'm understanding it, RCC run is something that we would use even if we were looking at a different source project, and it's like the configuration for cloud resources. And RCC run demo is the application that we're testing.
Correct. Yeah. So if you were to translate this to your own project, our recommendation is have some subdirectory where you would put a lot of this testing infrastructure. So what we're calling it here in RCC run demo is CI. So this guy here. And the key ingredients that you need are the cloud build pipeline, a variable file for your cluster, so you can define the environment you're going to do your benchmarks on. You'll need that RCC run configuration, and then any collection of batch scripts. So like, I think in the Spectra element code project that we have, let me actually pull that up so you can see how that's organized there, because that one's actually, it's more of a real application. So we have a CI directory there. I've got a few different types of cloud build pipelines, but we have our benchmark, right? We do the same kind of thing, build a Docker image, create a singularity image, and then call RCC run. And the way we did the Singularity exec there was we just set up like a file with a command line interface to toggle between like various binaries that we use for testing. If that makes sense. So like all this stuff does translate, and you're absolutely right. So RCC run itself is what you would want to use to basically provide that Docker image so you can call it from Cloud Build. And then yeah, it has a module to set up your Google Cloud project.
So in the demo that you just showed, that's another application that we could start to run with the same RCC-run kind of infrastructure.
Correct. Yeah. And the I think we have again, there's on our documentation, there's a very easy quick start. And it goes to again how to set up those basic ingredients in your own repository. So it's a bit more generalized. The assumption here for the tutorials today, I was going back and forth on whether we should try to like have people bring their own codes. But that kind of like activity with a lot of people is definitely something that we typically would spread over like a 3-day like mini hackathon, just to help people add these things to their application if they wanted it that way. But yeah, essentially for your own repository, you would be looking at adding Cloud Build, cluster config, so the RCC TFRs, RCC configuration, and then the Singularity exec. If you did dupe this TF directory underneath there as well, you'd be able to use this whole scaffolding under RCC run demo. If you just copy it into your project, you should be able to follow these steps to get your own source code set up to start. Now, I don't know. Yeah. And I don't know like where folks are at with containerization either. Cause like if you think about like, if you were to assess readiness for someone to get started with RCC run, I would say at least having a scripted build process to begin with, even if it's not containerized, is like level 0. And then level 1 would be either have a Singularity recipe or a Docker file. And then you would graduate essentially to that third step of adding Cloud Build. Once you have Cloud Build, the fourth step would be, doing the stuff we're doing here. So what we're at in this process is up at step 4. We've given you a repo out of the box that has satisfied levels 1 through 3. Okay, so right, we need to customize I think we already did this guy here. Let me just double check. Yeah, we added RCC TFRs. So now we can customize. Let me actually check in and see where we're at on our build. We'll also expand that and drop down to the bottom. So this is good. This is actually running the test now. So like you can see in what I'm showing here in the Cloud Build logs, RCC run did go through and actually set up the cluster. All right, so we're done provisioning. It does a SSH connection test. It tests for an active Slurm controller. If it fails those 2 tests after a certain amount of time, RCC run will terminate the build and deprovision those resources. So if there's ever anything wrong with RCC run or with your project's configuration, that would likely cause that to stop there. And then it does basically transfers the working directories in Cloud Build up to the cluster. And then it keeps an eye out for results file, which looks like it actually found one already. So it finished running the CI test. So now it's bringing the data back into Cloud Build, and it's going to deprovision resources. I'll quickly hop over to Compute Engine. So again, products and services menu. If you hit Compute Engine, you should be able to see a Slurm controller up that was provisioned by that system for you already. What we missed while we were talking was the controller itself. When it got the sbatch command from RCC run, the controller spun up the compute nodes to run the job. So we did miss that there, but we'll have another opportunity here in a minute. But yeah, if I go back into Cloud Build, which another quick way to get around in Google Cloud, Up on the top in the middle, there's a search for your products. If you were to just start typing in cloud build, you should see it come up there. So we're at about 10 minutes, 22 seconds. Let's see where we're at. Yeah, it's still transferring data back. So we'll let that keep running and we'll focus on customizing our cluster here. And then I'll show you where we can look at where the benchmarking data went. And then we'll do one more build where we'll test on the AMD EPYC Milans. Okay. So we need to add a new partition to the benchmarking cluster. And I do apologize, but there's not really a way for me to make things much simpler while also providing as much flexibility as we do. So it can be overwhelming at first looking at this RCC TFRs file, but I want to just kind of guide your attention to one specific section of that RCC TFRs file. So we're going to open this up. So again, from the RCC run demo, repository will go to CI RCC auto.tfrs. And there's a section that starts with partitions. So let me turn on line numbering here. Whoops. Okay, so starting down on line 23, you can see the partitions. We've got name and machine type are the two fields we're going to be messing with today. As you can see, there is a lot of options, and I think that we have 21 options to really identify what it is you're running on. If you were interested in using GPUs, we do have that GPU type and count there. I would encourage you, I think we dropped some links in the code lab that talk about the different machine families before you start venturing out from what we're going to do today. Take a look over that documentation because there are some restrictions on like the machine types that you need to have in order to attach a GPU to it. There's information like that kind of floating around in Google Docs. But what we're going to do is we're going to copy the C2 standard 8 partition, so the Intel Cascade Lakes. We're going to add a second partition to this dictionary, and we're going to set it up to use the they're called C2Ds. Those are the AMD EPYC Milans. So we're going to copy lines 24 down to 46. That's 22 lines. And paste it down below. So now we have a partitions block that gives us two machine types. So we have the option to have a C2 standard 8, and we have an option to have a, here what we're going to do is C2D standard 8. And the C2D, again, it's a machine family that gives us AMD EPYC Milans. And the 8 just means we're going to get 8 virtual CPUs. Now, the reason why I'm keeping these machines small is the quota on Google Cloud, which is basically, you could think about like when you get on an HPC cluster, right, you're usually asking for a certain number of vCPU hours or GPU hours. On Google, you have to set what the maximum amount of virtual CPUs, GPUs, disks, et cetera, that you want to have access to. And on all these projects, we've kept it fairly low to keep costs down for the training. But just keep in mind, like the C2Ds, you can go up to 112 if you needed 112 virtual CPUs. And you can change the number of nodes. So it's provided you have quota, I could set this to 100 and get myself running on 100 nodes, for example, for a benchmark, should you want to do it. Again, today we're keeping things small just for demonstration purposes. But again, check out there's the machine families documentation that we reference in the code lab. It'll tell you all about the different like sizes and shapes. And by shape, I mean like the ratio of memory to virtual CPU count. All of that is highly flexible. Like I said, there's a lot of other options here. The other one we need to point out is the zone. Because all right, so Google's resources are organized into various data centers around the world, and the data centers are grouped into what are called regions. Regions are sets of data centers that are geographically close together. usually within 100 miles of each other. And which specific data center in that region is what we refer to as the zone. Now, not all zones have C2Ds, and not all zones have C2. So if I were to do this partition, I need to have a way to set that zone so that we can make sure we're deploying our cluster to a region that supports both these instance types. Now, anything inside of these carets, there's really I think there's like a dozen of these variables that RCC run looks for in the RCC TFRs file. Image is one of them, so the virtual machine image that we use for those compute nodes. And like I said, the zone, which we're going to control here in a second through cloud build. So when RCC run digest this file, it's going to look for template variables like this. It's going to fill them in based on command line options that we send to RCC run. So we can kind of have that sort of runtime tunability. Now, I went ahead and looked around at the data centers that are available, and I know that US Central 1A supports both C2s and C2Ds. Now, by default, RCC run uses US West 1B, which only supports the C2 instances. So at the bottom of the cloud build file, what we're going to do is add a substitution variable for setting the zone, so we can control that when we trigger a build. So in your cloud shell, we're going to open up that CI cloud build.yaml. Below timeout, or at the very, very bottom, very, very bottom, we'll add substitutions, we'll add zone. And any user-defined substitution variable has to start with an underscore in cloud build. So just keep that in mind, which is why, and that's also why we're doing this for zone. And then what we want to do is in the RCC run build step, there's a flag for setting the zone, which is called zone, and we'll set that equal to that environment variable. So this allows you to control through the build process which data center you're going to deploy this cluster to. And again, this is usually needed when you start to use GPUs or some of the compute optimized instances, the C2, C2Ds particularly. You just want to make sure you get that right. All right, so what we've done so far is copied in a TFRs file for the cluster. We have added this C2D standard 8 partition. So now we have AMD EPYC Milans and Intel Cascade Lakes to test on. We've added a substitution variable for the zone, and we've passed that substitution variable to RCC run so that we can control where that cluster goes to. The last thing we need to do is add another test, or you can modify the existing test to change that partition to the C2D standard 8. So we're going to go back into that RCC run.yaml file. Okay, I'm going to go ahead and add the test. So we're going to run the two simultaneously. And the reason why I know they're going to run simultaneously is because the command group I'm giving to the second one is different than the command group given to the first one. So the other benefit of using these command groups in this way is if you have multiple tests that are independent of each other, you can use Slurm SBatch to basically schedule them all out and have them run simultaneously. So you're not going to add to those cloud build minutes. Just again, kind of nice if you're looking to save that money. So right, we got a command group now for smoother C2D for running on the AMD EPYC Milans. We got a different output directory now, and we're using that C2D standard 8 partition. We'll go ahead and kick off this build. And this time, in addition to adding the async flag so that we get the terminal back, we're going to use substitutions like we did before, but we're going to substitute in this custom variable that we got for US Central 1A. All right. How's everyone doing so far? Are we hanging in there?
Still editing that last file.
Okay, great. So I'll just again do a quick recap of what we just did, because I know this last step here was quite a bit of changes. The idea here is, with these kinds of setups, once you have something that works for your team and for your code, most of the time you're not really modifying this too much. It's just a lot of this just upfront work you have to do to get a repository set up to use this. So right, we brought in the default TF-bars file that RCC run provides, and we've added an argument to override that default. We've modified that TF-bars file so we now have a second partition to work with. Because we need to deploy to a different zone than US West 1B, we've added this substitution variable to the build process, and then pass that substitution variable to RCC run so we can select the zone during build time. Last, we modified the RCC run configuration to give ourselves another test. We're going to basically run the exact same container, the exact same command, just on a different machine type. So again, if you have that kind of pattern in your project where you need to be testing across multiple platforms, this is a fairly common way to set this up with RCC run. And last, we went ahead and gave it a submit here. So I'm going to hop back over to the cloud build panel, where you can see the build we had submitted first had finished. Okay. Down at the very bottom, you will get a summary report for each command group that shows you the basically pass-fail percentage. If you do have any failures, RCC run will surface a non-zero exit code so that the cloud build also fails. So if you're using cloud build to relay information back to GitHub, for example, for pull requests, you'll be able to integrate just like you do with GitHub Actions. A particular check in cloud build failed, which is pretty nice. Now that this build is done, we actually now have data in that BigQuery data set. So I'm going to go back so you can see our new build is currently running. In that search bar in the very top center of the console, we're going to search for BigQuery. Okay. So again, up on that top there, the products and pages, you'll see BigQuery. On the left-hand side, underneath the Explorer, again, we'll hop down into that app runs table. So it should be your project here, then the RCC run data set, and then app runs. So right now we're looking at just the schema, which tells us again what columns we're going to have in this database. If you look at a preview, you should have one row in there at this point where it's going to tell us, it pulled from Slurm. Hey, I had 8 CPUs allocated to this job, no GPUs. Some of these fields that are optional with RCC run are going to all be null. But you see our batch options are here, command group. If you scroll to the right, compact placement and GVNIC. Those are 2 features on Google Cloud. Compact placement is a flag that you can set to basically request to Google's scheduler that you want to have those compute optimized nodes close together physically within their data center. So within, a Google data center, these machines are likely, pretty far apart, but if you add that compact placement, the Google scheduler will try to get them close together. So if you have MPI applications, this is certainly something you want to play with. If you have applications that require lots of network bandwidth and are not necessarily latency sensitive, GVNIC is ideal. So those we both set to false here. We're just doing serial applications in this demo. We didn't do anything fancy with the file systems. So there's no file store, no Lustre information populated. But if you keep scrolling over, there's our command, our unique build ID, the machine type we ran on, GPU count, how many nodes were used. Now this is what's kind of nice is if you have the node count and you have the machine type, you can actually merge this data set with Google's price book data set and not only get runtime, but you can actually get estimates of simulation costs, which if you're on the cloud, it's really important to keep track of not just performance, but the actual dollars you're spending on running a particular simulation. And I was surprised to learn how complicated that relationship can be for some applications. So keep that in mind. We have a date timestamp. So when you're analyzing data, if you wanted to pivot off of that column, that information's there. We got exit code. Since we had a manually triggered build, the get SHA comes back as empty. The amount of memory that was used, or the maximum amount of memory that was used, as read by Slurm. And then we've got our runtime. Of course, that VM image is there. So again, we have a full description of the environment that we ran on. And from having the version and build information, we know we are able to recover all the information we need to recreate that exact benchmark. So, you know, the intention here with RCC Run, of course, is helping folks do this kind of analysis of performance portability, help them assess costs on Google Cloud for their specific application or on their on-premise resources through federating a Slurm cluster. But of course, enabling that reproducibility side. So if someone wanted to redo this exact benchmark, you have all the necessary ingredients to recreate it. So let's take a look back at how we're doing on the build. So we'll look up here in the search bar again. Take a look at Cloud Build. And we're about 6 minutes in, so we should have a cluster up at this point, I believe. Yeah, it's checking for a results file. I'm going to go ahead and hop into the compute engine panel to show you what's going on there. So we should be able to see a compute node here in a second. So we'll go to that navigation menu on the top left, drop on down to compute engine. And you see we got our controller, and now we have actually 2 compute nodes that are live. And again, all this is being controlled by the system, so you're not having to manually do, you know, instance creation, all that stuff. Again, all that stuff's handled by RCC Run, and a lot of the environment we've put out images for you for free, so that you don't have to worry about at least getting started. Now, if you have nuances for your application, again, specific MPI flavors, CUDA version requirements, those kinds of things, you will have to do some customizations to meet those needs. But it's not a huge leap to go from this kind of setup to something like that. We'll go ahead and let that run. And while that's running, since we have some data to look at, when we have a little bit of time here, thankfully, we're going to hop into Data Studio, which is not written into the code lab because most of it is, there's not a lot of actual coding to do, and it's really hard to drop what we're going to do next into a code lab. So, but if you do go to that page 9, the congratulations page, because you've made it this far, we're going to open up Data Studio, which is a free dashboarding service that integrates with those BigQuery data sets. So you can create a live dashboard that keeps track of all this benchmark information for your application. Let's go ahead and open that up. And we're going to create a blank report. Now, there's going to be some basic info here. This is tied to that training account. So don't feel like you need to put your personal information in here. If you want to, for a company, I would put either ISS or water change for today. And just hit agree to those terms of services, and then just hit no on all these other bits there. So again, we'll hit blank report one more time. And you should see a page that looks like this. We've got an untitled report, and what we need to do is connect data to Data Studio. Now, there's a lot of different ways you can get data into Data Studio. I mean, if you scroll down, you'll see tons of different services that are compatible with this dashboarding system. We're going to use BigQuery, which should be in this menu on the top right. If you click on BigQuery, It's going to ask you to authorize. And again, since you're using the training account, it will only pull up the project you have access to right now. So you hit that project. We'll add the fluid CI/CD data set and then app runs table. So again, I'll go back from the add data to report. You'll hit BigQuery, hit that project data set, and then app runs, and then hit add down in the bottom right corner. Okay, go ahead and add that to the report. And in just a second, you'll see on the right-hand side that entire schema from the BigQuery table populate on the far right side. So you have access to every bit of data that's in that BigQuery data set. I'm just gonna do something simple here because everyone has their own questions and what they want to look for in data. But I just want to show you how you can move around in Data Studio just to get the basics going of how to keep track of runtime, and then give you some drop-down menus so that you can select date ranges and select a Git SHA. So what we're going to do on the right-hand side, you have the data source, which is that BigQuery database that we just connected. So we don't need to modify that. It already picked up the date time column as the date dimension. So we've tried to set all these fields such a way to make this process fairly easy to get started in Data Studio. Now the dimensions that we want to use, today I'm just going to go ahead and pull in. If you were, for example, to click on the dimension that's there, you can search for any column that's in that BigQuery data set. So we'll say machine type. So you can see our C2 standard 8, and actually looks like our other run just finished because now I have the C2D standard 8 in there. I'm going to go ahead and add another dimension. Let's say allocated CPUs. I'll go ahead and make this wider. What else would we want to look at? Let's say command group. Okay. And you might have execution command. So let's look that guy up. All right. And then down in the metric. So the metric is going to be a numeric value that is aggregated in some way as a function of these 4 dimensions. And by aggregate, what I mean is we're looking at a minimum, a maximum, median, a mean, or a sum of some quantity. Right now it's set to the record count. So it tells me I've got 2 records that are C2 standard 8 with 8 allocated CPUs for the smoother C2 command group for this specific execution command. But what I want to see is runtime. So I'm going to swap out the record count. We'll do a search for runtime. And then rather than looking at a sum, because since I had 2 records for C2D for the C2 standard 8, it's actually adding up the runtimes for all the runs that match this criteria. I'm going to change that to a maximum. Okay, so now I can see, okay, if I run on AMD Epic Roams versus Cascade Lakes for this application, for these command groups, I know I'm taking 13 seconds for each platform. All right, so now let's talk about how we can customize this a little bit. Let's say, for example, in your summary report, you don't want to see application runs that failed. Because right now, there's nothing that's filtering out a failed run from this, and it could skew your data in a way that's not conducive with what you want to convey. If you scroll down on the right side, down to the very bottom, there's a filter option. If you add a filter, we're going to set up a filter to get rid of non-zero exit codes so that we can only look at in this table runs that did not fail. Now, in this case, this is not going to have any impact because the demo runs we did both succeeded. But let's say, you're in a scenario where that's necessary. We'll go ahead and set this filter up. So we'll call it passing runs in the name field, not rune runs, passing runs. And we're going to include, if you look for exit code, so you're going to include exit codes equal to 0. So this way, again, any run that fails, it's not going to show up in this particular page in Data Studio. Again, it's not going to have impact here because all of our runs passed, but that filter is on. And now we can do something else. We can add controls. By default, looks like it gave us a command group to control, but let's say I wanted to change that to machine type. So if I wanted to be able to dynamically change what I'm displaying here through a drop-down menu, if you select that control we just added, in the control field on the right-hand side, we can change that from command group to machine type. So now I can select, like, so for example, if I just select C2D standard 8, you can just filter that down. Right, so you can do this for any of the columns that are here in this view, or any of the columns that you still haven't imported in. So you can filter down that way. If you want to add a date range controller, again, up on the top, add control, date range control, and drop that in. A common setup. So by default, what's going to happen with the date range controller is it's going to try to bring in as much data as Data Studio can handle. So it depends on, in terms of how far back it goes in time, is going to depend on how frequently you commit or test, those kinds of things. What I like to do is just set it for like the last 30 days, no matter what, or the last 7 days. Timescales are, again, things that depend on a group, your own team, and what you want to see. But if you wanted to customize that, when you have that date range selector selected on the right-hand side, you should have an option for setting the default date range. When you click that drop down, a calendar pops up, and up in the top right corner of that calendar, there is an auto date range, and it gives you a list of options to choose from. So let's say I did, let's say last 7 days, and I want to include today. So we'll check this box to include today. And so every time I open this report now, it's only going to show me the last 7 days, including today, of information. Now this table, as you get more information in your database, can get kind of unwieldy. So you can change this from a table to like a bar chart, fairly straightforward. It's up on the right where it says chart table. You can click that drop down to get all the different types of graphics that you can use to display that data. So let's say I did a column chart. And so what it should do from here, you see on the x-axis, we have the machine type. That's set by the dimension. Right now, it's controlling based off of the allocated CPUs. It's what's called the breakdown dimension. But you could also, what we do with self is look at compiler. If you wanted to group by compiler, for example. Here we don't have that set, but this should get you kind of started with the various ways you can dive into the data. I'll show you an example of what we've done with another application, just to spur some ideas for you if you go forward with this. This is for the Spectra element library in Fortran that I showed earlier. Get this guy over here. So we've set up a few pages. So on the first page, we have a pass-fail report. Let me actually drop this back so you can see some of our failures. It's always good to show those. So what we've done is made a little table that pulls together when a failure happened, which command group it's in, which execution command caused the failure, so I know how to reproduce it. And then I have the STD error, so I have the log of what went wrong. So in this case, I hit a segmentation fault in HDF5. So when you hover over, even if the STD error is a lot of content, when you hover over, a tooltip box can show up and show you what that error was. So it's, again, a very convenient way to start to isolate which one of your benchmark tests are failing and figure out what went wrong. Of course, you can also couple this with on what machine type with what compiler, and you have all that information aggregated in one place. We did another page with runtime. We did a little bit more complex view than just a column chart. This is called a pivot table. We have the command group and execution commands setting up these two column and subcolumns. So I have underneath the S3D interp benchmark that we run, I've got a few different types of execution commands that are grouped under there. And then on the columns, I actually have the different machine types we're looking at. So I can just look at how performance of my various benchmarks change as a function of the platform I'm running on. Runtime is great. On cloud, node seconds is better because node seconds, there's not a whole lot of data here. But node seconds is more in line with what you would see as a cost on Google Cloud, because you don't pay just for the vCPU. If you reserve a whole node, you're paying for that whole node. So we use this really as our proxy for cost tracking. And we do have a pretty detailed tabular view that has a lot more columns in it, just in case we're trying to dig into something to look into on any of the other reports. So that being said, if you did want to add other pages, up on the top of Data Studio, if you hit Add Page, you'll now have the option to basically create as many different views as you want off of that database. So I am running out on time. In the last 5 minutes, I'll take questions. If you have them and you want to share them on Slido, please do that now. Or if you want to unmute yourself and we can chat a little bit, I'd love to answer any questions you have.
Thanks for the great demo, Joe. Maybe I'll start us off with the questions. I'm just curious, when you talked about the options that are there to try to maximize, say, like node locale or node proximity, and also the NIC setting, are those, do those have any cost implications, or are they just sort of time to run? And then I guess B, is there any sort of easy metric there to determine how successful GCP was at actually giving you nodes that are close together? And
that's a very good question. I'll answer the cost question first. So compact placement does not cost anything additional to just scheduling the resources. GVNIC does cost. It's not a huge amount. I'd say it's about 1% of the actual of a vCPU cost. It's very small, but it is additional. So you definitely keep that in mind if you use GVNIC, that you'll see a bump in compute costs. So GVNIC is a feature that it just opens up more bandwidth on Google's network. So if you're trying to communicate between two VMs and you have high bandwidth communication requirements, it can definitely help. And then compact placement, although it doesn't cost anything, if the scheduler cannot find a close set of nodes, it will more than you decrease the percentage of time that you'll actually get on a group of nodes. Now, that being said, what I can say is if you're up to like 10 virtual machines, most of the time I haven't noticed a difference in terms of compute node availability, whether I have compact placement on or off. When you get to like 25, 50, 100 nodes, you'll start to have some feedback from Google's scheduler that Slurm interacts with. It will have a harder time finding those nodes, again, depending on time of day and data center. So, your mileage may vary there. Now, the way around that is to do what's called a reservation with Google. So if you know you're always going to be using 100 VMs, you can purchase a reservation, which guarantees that you'll have access to a certain number of nodes. So if it's like mission critical stuff, you would probably want to have that. Now for builds, what I prefer to do is just like accept the potential for failure and redo, like have some logic in the background that just retries the job a couple times. So again, your mileage varies. Now in terms of whether there's a payoff, this comes down to scaling. So what we like to do when we start integrating applications with Google Cloud is start with all these features off and use a generic instance to give us a baseline of like, okay, how does it perform? How does it scale if you have a fixed size problem? And then, change from a standard instance to a compute optimized instance. And again, look at performance and scaling, and then turn on GVNIC or turn on compact placement and see what that sensitivity looks like. So that's going to tell you pretty quickly whether or not it's even meaningful to have compact placement. Now, this being said, the other honest truth I can tell you is if you have 100 nodes that you're running on, probably not even worth adding the compact placement flag, because you're likely taking over a significant portion of a data center, and you'll already be fairly close to each other if you're using 100 nodes within the same zone.
Okay, thank you.
Yeah.
Let's see, do we have any other questions on the Slido? But anybody can feel free to unmute and ask Joe a question directly.
Yeah, so the last note I'll add is we'll keep those training accounts open for the day. Expect that over the weekend, those accounts will be deactivated. But the code lab itself, the RCC run demo, RCC run repositories, again, are all public, open source. You can use those as you will. And there are contact information on those repos on how to reach out to us. If you have questions, we have a community support channel, which sometimes it can take us a little bit to get back to, but if you just email support@fluidnumerics.com, we're happy to help folks there. Or if you just open an issue on any of those GitHub repositories, we're pretty diligent about keeping track of those.
All right, great. Well, I guess if there aren't any questions, please give Joe a hand. That was a great presentation and a great demo. We're going to take a 10-minute break, and then we'll come back for one talk at the end of this session before lunch. So we hope to see you back at 10:30 Mountain Time. Thanks.
This meeting is being recorded.
All right. Well, thanks everybody for rejoining us for the last part of this morning's session. We have one talk before lunch. The talk's going to be from Edward Hartnett. Edward is a software engineer at the National Oceanic and Atmospheric Administration. Just a reminder to everybody that if you have questions, please put them in the Slido and we'll take those at the end of the talk. So with that said, Edward, please go ahead.
Hello, thank you everyone for your attention. I'm going to be talking about improving the documentation testing process and code for a bunch of NOAA Group 2 libraries. I would like to acknowledge my collaborators, Hang Lei, Brian Curtis, and Kyle Gerheiser, all work with me at NOAA EMC. And we have spent some time on the GRIB libraries. The NOAA GRIB libraries are about there are 7 repositories. It's mostly Fortran 77 code, and it does a lot of reading and writing of GRIB 1 and GRIB 2 message files. GRIB 1 and GRIB 2 are the WMO data format standards for weather data. And even though NOAA internally uses NetCDF almost exclusively, there are still uses of GRIB data, both reading and sending out. And so these libraries are still used in the NOAA forecast, or as a result of the NOAA forecast. NOAA has their own GRIB code tables. One of the things about GRIBs is, unlike NetCDF or HDF5, it also includes the concept of code tables, which have to be maintained separately of the data file, and therefore can cause a lot of, and indeed do cause a lot of confusion. And these libraries are kind of where NOAA maintains its GRIB code table information. When we started this project, there was essentially no test code for any of these libraries. And it should be mentioned that the staffing on this is quite light. We don't have a lot of people here. So there's about 150,000 lines of code. And this is important code. And even though it has not been historically tested well, it's still used every day and needs to be maintained properly. So we've made progress in these areas here, and I'm going to talk about each of them as we go through. Let's start with documentation. As with the rest of the NCEP-libs libraries, we converted the documentation that was in this code to use Doxygen. So Doxygen is a tool. It's very popular in C and Fortran projects. It keeps your documentation with the code, and lets you use things like Markdown language and HTML if you like. And then the build will generate a nice web page documentation, and it can be hosted for free on GitHub. And I'm going to explain a little bit about that. During our documentation process, we were greatly aided by the fact that there was a lot of really good legacy documentation with this code. It was following a predetermined format, and they were pretty rigorous about it. And so we had a lot to work with here, and that was great. Documentation benefits the three different categories of stakeholders in the software. From the programmer's point of view, if we have good software in Doxygen, it makes it easier to debug code and to work with the code. And it also makes it easier to communicate effectively with others, which means less meetings, less interruptions. From the supervisory layer, good documentation helps communicate with users and also captures legacy knowledge, so that programmers who work there a long time and then they leave, if they've documented their work all along, then that's obviously a lot easier to cope with. And it's also easier to add staff to a project. When you add staff to a project, if there's no good documentation, it's hard for them to come up to speed. So having good documentation allows to be able to add staff more quickly to projects. As far as the science community is concerned, when these tools have good documentation, it's easier for the external scientist who's using them to code without making a mistake. So if we do not have good documentation, it might be easier, or will be easier, for that scientist to code in a way that's incorrect, and then their science results will be polluted by using this library incorrectly, and that's not what we want. Okay, so on the left part of the screen is some output from the Doxygen build, and it shows up here a project name and version. And then here we've opened up a list of files and clicked on one, and it shows the documentation for that file. And this is a sample. I have several other samples. This is default formatting for Doxygen in terms of the colors and the fonts and all, and that is what we've used. But it is possible to use style sheets, and I'm sure they look very nice. I just have never tried it. One thing that Doxygen gives you is that it does an automatic hyperlinking of many things, like function names are automatically hyperlinked to their documentation, so that's helpful. And it does allow you to add formatting elements, like here's a bullet list. There'll be more later, and these are easy to deal with. Images are also possible if you have some slides or what have you that you want to put in your documentation. That's quite easy to do. Here's a little more detailed. So in the background here, we have some Fortran 90 code, and we see how Doxygen comments are created using these special comment characters. And we also see Doxygen tags, which are special things that you can put in there. In this case, the author tag allows you to specify who wrote this particular file. And over here, you see how this is rendered in Doxygen. Note, for example, that the variables have this special comment, and then they have a little bit of documentation here, and then that appears here in the documentation. So you get nice documentation of all of your variables and your modules and your functions pretty easily. And as you can see, it's all kept right by the code. So if a programmer is modifying this, it's very easy for that programmer to update the documentation at the same time. Here is another example, and this example has several layout details. Up here is a numbered list, and here this will turn into a table. So when you use these characters here in this way, it turns this whole batch of text into a nice looking table. And here this will turn into a bullet list. And now if I show what that is rendered as, you see up here is the numbered list Here is the nice looking table. And here is the bullet list. And here you can see what the effect of the author tag is. And there's a date there as well. So how does one add Doxygen? It's not hard. You add a docs subdirectory. You have to add a doxyfile.in, which contains a bunch of settings that are mostly boilerplate. And then in our case, we added a user's guide document to each project. So each project has one user's guide that's kind of like here's a general introduction to the whole thing. And then each function, module, and module variable is documented. When the project is built, the doxyfile.in is turned into a file called doxyfile, which is what Doxygen actually uses. So it's possible to set various things about the documentation in the configure step, if that is of interest. And when you're done and you've built your documentation, there's a feature on GitHub which allows you to put it up on the web for free, which is very nice. So here's a little, I realize you probably can't read the text, but that's okay. This is part of the README file for this project. And somewhere here it says, for full documentation, see this. And when you click on that, then you get the full documentation for that project and that version. And that's enabled using GitHub Pages. This is the settings. We'll see a little more about that. So in the Doxy file, which controls the settings for Doxygen, there's some important settings. There's hundreds of settings in there. Most of them can be completely ignored, but this list here should be looked at. And here's one that's important, or these two. To turn on more warnings, you set this one to yes. And then if you turn on this warn as error, just very similarly to the way compilers have a way of saying any warning should be treated as an error. So this will do for Doxygen, and therefore you can set this once you've created warning-free documentation for your code base. And then if anyone tries to do a pull request with incomplete documentation, they will generate a warning which will error out the continuous integration build. And so you can check to make sure that everyone is submitting enough documentation with their new code. So how did we do? How have we done so far with our GRIB libraries and documentation? Well, all of our GRIB packages now have pretty excellent documentation. We're checking for documentation warnings in continuous integration, so new contributions will have good documentation as well. And that is ensured by reviewing documentation and code review. We can check that all the elements are there, but we cannot check that they make any sense. So we have to look in code review to make sure the documentation that's being submitted actually makes sense. And further progress is quite possible, but we're moving on to other elements of the code now, and I don't know if we'll get around to making our documentation any prettier in the short term. Okay, so now we'll turn to the topic of unit testing. Testing is a very necessary part of the modern software practice. You really can't have agile code and continuous integration without good unit testing. And if you have those things, if you have good testing, you can develop a lot faster. That's the point. A test is really just a program that uses some of our code and then exits with a 0 for success or non-zero for failure. And that's easy to create. And I'll demonstrate a little bit of that. And once you have tests for your code, you can measure automatically how much of your code is being tested. And that helps you to identify gaps in your testing and fill them in to make sure you have good testing. Now, with this code base starting from basically 0 tests, writing all the tests that we need is a very non-trivial task. We're certainly not done. We've made a lot of good progress, but there's a lot more for us to do here. Unit testing benefits all 3 categories of stakeholders. For programmers, it makes life a lot easier and less anxious because code can be changed more confidently and more quickly. For supervisors, it means less stupid bugs and less time spent on rework. And it also captures legacy knowledge, because putting in a test for code along with the code in the documentation is very helpful in expressing what that code is supposed to be doing. And for the science community, testing really leads to a much higher quality code. And if you're using some library as a black box, you really want it to work properly. You don't want to be debugging problems within a black box. That's the whole point of using it as a black box. So what is a unit test? It's really just any program that is distributed with your code and built by your build system, and then can be run by people who have built your code. And it may use test data, and it may not. It may create its own test data. If you have MPI tests and MPI code, it's certainly possible for that to work. It takes a little extra effort. So unit tests are just programs in Fortran or C which call library functions and then look at the results and make sure they're correct, and then exit with a 0 for correct or non-zero for failure. So they're quite trivial. Here's an example of what I mean by returning 0 or non-zero. This is from C. I have a Fortran one coming up. And in C, we define, in this case, an error macro, which takes a number and prints out some message and then returns that number. And so if you call this with a non-zero number, it would return a non-zero number to the operating system. And here we see we're calling our library function, and we're checking the return value. And if it's non-zero, we're erroring out. So this will cause the entire test to stop right here with a non-zero return value, and that will cause the whole test process to stop right there and say something failed. It's important to note that test output, in terms of whatever the test is writing to the screen, is unimportant except for debugging. No human should be involved in looking at the output and determining whether the test passed or failed. That has to be detected automatically. Similarly, for Fortran, we have a little subroutine check, and you pass a number, and if it's 0, you can do a little something and call stop 2. So that returns with a 2 instead of a 0, and that's how this code knows that if it gets a 2 and returns a 2, the test failed, and that has to be counted as a failure. It doesn't matter what non-zero value is returned. 0 means success, any other value means failure. So it doesn't really matter what you use there. So once we have tests, and we do for some of these libraries, then the question becomes what still remains to be tested. And for that, there is a tool. It's built into GNU compilers, and you turn on a couple of magic compiler flags, and then you get some output, and that shows you, in this case here, a list of the code files involved in this library. This is from the G2C library. And then it shows you how many lines of code within that program file have been run during your test run. And the green, yellow, and red are obvious cues. Red means you are not testing much of this file. So in this case here, we're only testing 26% of the code in this file. So that clearly indicates we need more testing there. In other cases, we have achieved 100% testing, which is not always possible, but it was in this case. Now, if you click on the file name itself here, you can dive deeper. And here it shows lines of code which have been tested in green and lines of code which have not been reached by testing in red. So you can look at code like this and you can say, well, is there any test I can construct that will cause this if statement to be true and therefore this line of code to be run during testing? And this is an error condition. So that brings up the point that with Fortran code and with C code, there are some lines of code, like perhaps this one, which it's not really feasible to reach during testing because creating the error in the right place, it would just be too much difficulty. And that's fine. So if you don't achieve 100% testing, that's why, and that can be okay. But what's important is that you achieve as much testing as you can feasibly achieve. So where do we stand with our GRIB libraries and testing? Well, we all now have at least a token test, and we're running continuous integration. And that's good, that's progress. We've added a lot of tests to some of the libraries. We've added a lot of tests to G2C and to G2. We've added some tests, and other libraries have not received as much attention. We are focusing on the GRIB2 libraries first, because they are used much more, but there are still some important GRIB1 applications. And even though everyone tells me it's going to go away, it's not clear when that really will be. It might be years from now. So I hope that after we get the GRIB2 code well tested, we can turn our attention to the GRIB1 code and start putting some tests in there too. Now, this is a very active area of effort, so we're not done yet. More testing will come. Okay, so now I'm going to talk about continuous integration. And continuous integration is when you run all of your tests automatically anytime someone wants to change the code. So you have a bunch of tests, and the computer programmers can run those manually and get a pass-fail. But what continuous integration provides is every single time someone wants to change the code, it automatically runs a whole suite of tests. And unless those tests pass, you cannot merge that code. And that is an extremely helpful tool for keeping your code release ready at all times. The continuous integration that we are using here is hosted by GitHub, again for free, and it's very useful and easy to use. In the previous presentation, we saw some use of a fairly complex setup for running CI, but in this case, we're using very simple GitHub actions, and they're working fine for us because we're not trying to do, obviously, what the previous presenter was doing. And what are the benefits of continuous integration to the different categories of stakeholders? Well, programmers experience it as catching their mistakes much more quickly and also without someone else noticing it. In other words, it's much nicer if you make a mistake to find it yourself than to have your manager point it out in the meeting. So continuous integration is constantly catching all your mistakes before anyone else even sees them, which is terrific. And it also runs a bunch of things that you could run from your command line, but you're too lazy to do so because it's a bunch of effort to set them up. But in continuous integration, they're all set up all the time, and it can run 5 or 6 or 10 different configurations and test them all, and you don't have to do anything except look at the results. So that's super convenient. From a supervisory point of view, it prevents regressions, which is when something worked and then it's not working anymore because someone broke it. If you have good unit testing and good continuous integration, then you will never have a regression because anything that breaks will never be committed. And it also makes it a lot easier to do releases when you need them, because if you have continuous integration and you're checking every change to make sure it doesn't break anything, then you can do a release at any moment. Whereas if you're checking in code that can break something, and then you want to do a release, oh, well, now you have to fix that first, and that can be a real pain. So it keeps your code release ready at all times. For the science community, tools that are developed with continuous integration will be more reliable. And when you upgrade them, it's much less likely that something won't break. Because if you have a body of tests that you're maintaining and using continuous integration, and it comes time to do a new release, by definition, everything that worked in the last release will work because you have tests for all of it and you're running them every single time. So that way, science users can upgrade to a new version of your software without fear that you're going to break their expensive science system. Here's an example from a GitHub workflow file, and I'm not going to go into it in too much detail. I just wanted to show that at a certain point, it just becomes a set of bash commands that you type in just as you would do from the command line. And so here we do a little setup, and then we do a CMake to build our package with a bunch of options, and then we do a make, and down here we do a make, we do a C test, which just runs all the tests. So this is just as you would do from the command line, and you put it in a GitHub workflow file with a little bit of magic. It runs every single pull request. And if you're interested in further details, you can look at these online. I provide a link to the packages. Everything's online, and it's not very hard to get these working if you're interested. I highly recommend them. So once they're set up, they're run automatically, and here's just a little screenshot showing what it looks like. The green checks indicate that in this case, all of them passed. And here you can see a little hint of what I was talking about before. We're running with GNU compilers. We're also running with Intel. We're running with a different version of a dependent library, and we're running a Mac OS check as well. So all of those run for every pull request. And as a programmer, you would be hard pressed to run all of these tests on your own code before you submitted a pull request. It's just not practical. And on larger projects and as things advance, this might turn to be 10 or 20 different variations of how the tests are run, and continuous integration will run all of them for you automatically, whereas running them by hand would take a lot of time and effort. So once you run your tests, then there's a way to get the output, and this is just showing some output of a test run. If it fails, you get a big red X, it's obvious, and then you can drill down and see what went wrong. The continuous integration supports the software process in a bunch of important ways. It doesn't just run all the tests, it also runs a bunch of other checks on the code, like it checks the documentation, it checks for warning-free builds, it can check for memory leaks, it can check for other versions of dependent libraries. Like let's say you want your code to work with the last 3 versions of NetCDF. Well, that's hard to test from the command line, but you can set that up in continuous integration so those 3 past versions are always run. And then you have confidence that you're not breaking anything. And as we saw, it can check on different operating systems. There's also Windows. We're not using it on these projects, but you can check on Windows if that's a requirement for you. And you can check with different compilers and different versions of compilers. There were a lot of changes in GNU compilers in version 9 and again in version 10. And so I believe in many cases we're testing with pre-version 9 and then with version 10 to make sure that everything continues to work. Excuse me. So how are we doing with NSEP gribs and with CI? Well, we have testing in place for all of these packages. We test on a lot of different operating systems, and we're continuing to work on our test code. So let's talk about software process. I think I'm overrunning my time here, so I'm going to have to speed up. We have switched to an agile software process on all of these projects, and that is working very well. Agile process benefits stakeholders in a lot of different ways, mostly by speeding up code development and taking out rework, and that's very helpful. We follow a well-defined process for development, which starts with creating an issue and then branching your code and doing your development. Then a pull request is submitted, it's inspected, and only after it's passed quality review is it merged to master, and the whole thing starts again. And when doing this, we use the GitHub issue, to gather requirements and discuss exactly what we feel needs to be done. Pull requests are then submitted, which document exactly what you're trying to do and allow a place for commentary. And we have a release process that supports full transparency so that when users are going in, they can see what has been done and why. All of our grip packages are now doing pretty well on following the process, and we're happy with the process of all these packages. We have done some refactors and improvements of the libraries as well, and those bring benefits to stakeholders. And I will let you read that from the slide there. But one thing that we've done is we've removed some unused code from the GribUtil package and from the BackIO library. And we always want to remove unused code because it's just adding to maintenance costs without adding benefit. We've switched our Fortran to free format to make it easier to work with. And we've used the ISO standard C Fortran layer instead of our previous kind of hacked way of doing it on a compiler by compiler basis. Currently, we're building 3 different binary instances of each package, one for 4-byte integers, one for 8-byte integers, and one for 8-byte integers, and 4-byte integers and 8-byte floats. And that's awkward. And we're trying to get a handle on that, but that's a challenging problem. We have done it for the BackIO library, and we hope to do it for the other libraries in the year ahead. In the future, we hope to further simplify this these systems, and reduce maintenance costs further because it's a lot for us to handle. Including, we hope, combining a few more repositories and combining some other repositories. We're not sure if we're going to combine them or not. They're similar code. It's under discussion what's going to happen with them. And of course, we know that we need many more tests, and we're continuing to work on that. That's all I have. Thank you all for your attention, and please let me know if there's any questions.
All right, thanks, Edward. Yeah, we're a little over time here, so I think we can probably address Eric's question here, but then we'll end the session. So Eric asked, can you expand on your use of GCOV for code coverage? At least I thought that was the basis of what you were using. Were the charts you presented from GCOV, or did you do some of your own post-processing of the data from the tool?
We did not do any. Yeah, they're all from GCOV. And if you look at our GitHub site, you'll see the commands that generate them and upload them to, we upload a zip file to, anyway, go take a look at the GitHub actions and you'll see what we do. But we did not do any custom coding there.
All right, thanks, Edward. And thanks to everybody for your attention for the morning session here. We'll take a 1-hour lunch and hopefully have you back for the final afternoon session of the conference. Enjoy your lunch.
Hello, hi team. It's Friday and it's the last stretch. So welcome back to the last stretch of the conference. My name is Maggie. I'm a software engineer at Cosmic, and it's my pleasure to present the last 4 speakers for the conference. So next, we're going to start with Dr. John Dennis, who is a research scientist at the National Center for Atmospheric Research here. And the title of his talk is Enabling Execution on a Graphics Processing Unit of an Idealized Atmospheric Model. So thank you. Welcome.
All right, thank you, and I'm happy to be able to present here. So, all right, so you know, when I initially put the abstract for this, I was going to do it a little bit more straightforward, but I decided to take kind of a little bit of a different spin on it, and so I wanted to talk about the co-design process for GPU enablement. And you know, our lead-off speaker, Irfan, discussed the co-design concepts. And so I kind of wanted to step through our experience with this particular application. So, you know, what is a co-design process? It's really how you match software, hardware capabilities, and scientific objectives. And so I wanted to, or we wanted to address why and how a GPU enablement project is initiated. I think this often goes frequently an undescribed piece of the project. Usually they show you here are the great results, and then they give you like a speed up result. And so we're gonna start this description by letting the science lead the software investment. And so here's some description of the science that we're trying to address. And really we're looking at how do processes at the air-sea interface affect large scale transport and dynamics. So what's going on here is that you have aerosols that are being lofted into the right above the ocean, so in the boundary layer. And we'd like to understand better how they interact with large scale climate and also hurricanes. So we're going to use a large eddy simulation, and we're going to use Lagrangian droplets for this. So this is going to refer to this as a Lagrangian cloud model. And so it's going to have the airflow solved using a traditional LES methods, but it's going to have two-way coupled feedback. And one of the challenges of this is that it requires many particles to resolve the cloud spray phase. And here's just I think this is a picture of clouds. So more specific scientific questions is how do coherent turbulent structures affect spray droplet transport, and do these droplets modify fluxes, temperatures, humidity in the hurricane boundary layer? And we believe that the Lagrangian cloud model is ideally suited for answering these questions. The plots there are temperature and vertical velocity. So we want to use GPUs to enable, we came up with the idea GPUs to accelerate the flow in the droplet solver. So what we're going to do is we're going to place an LES box and a idealized hurricane. And so as indicated by the image on the left there is the hurricane. And so we're going to place a little box, and it's going to have very high resolution, and then we're going to look at different surface roughness parameters and also different radiuses relative to the eye of the hurricane. So what's the tool available for this scientific investigation? And we're gonna use the cloud model version 1. This is an idealized atmosphere model, and it's designed for process studies of numerical weather simulation. So this is a Fortran code, uses MPI and OpenMP. We augmented it with a Lagrangian transport capability. It is CPU only, which is, or at least it was to begin with. And some of the computational characteristics really to address this scientific question was we really needed large resolution. So 2,000 points in the horizontal and 1,000 points in the vertical, and with very hot, fine grid spacing and a large number of droplets. There's a range of droplets. We're going to use as many droplets as we can possibly fit onto the system. And so the first question we're trying to address is this a GPU amenable scientific question? Because honestly, not all are. So this, but the good news is we have a very large number of grid points and particles. So this means that it could potentially be a viable GPU solution. Okay, so the first step in this co-design for GPU enablement is that is the science objective GPU amenable? And so the answer to that is yes. So next we want to see if the code base is GPU amenable and determine the potential return on investment of GPU enablement. And this is, I think, kind of a little bit of a things that people do and they don't really necessarily tell you about it. And so we kind of want to dive into that. And so we're going to dive into this by looking at code structure and kind of do a deep dive on there, because you can actually kind of get a hold of these by looking at code structure and reasoning about it. So this is the overall CM1 code structure, this big time stepping loop, and it has various physics and dynamics subroutines. And so we want to zoom in on one of them, the solve2 subroutine. And again, this is kind of pseudocode. It has, a bunch of loops, loop 1, loop 2, and also some other subroutines that do evection. So let's go in and examine loop 0. This is what it looks like. And so this is very useful actually, because a large amount of parallelism is available at the loop level. And there's an existing OpenMP implementation. So that means that people have already thought about what threading might looks like. So you say how much parallelism is available. Well, frequently these indices, the extent of these indices are like 256. And so the loop trip count through this triply nested loop is about 16 million. And the working set size of the loop, so this is the number of basically the total volume of variables that you'll be accessing, is about 256 megabytes. So 256 megabytes is probably likely going to miss in the L3 cache if you think of putting this problem on a single node. It's not going to, there's some CPU-based solutions that have really large L3 caches, but you may or may not get access to that. So what this means here is potential return is the CPU code base amenable? Well, yes, it is, because there's a lot of parallelism at the loop level. It's not, the parallelism isn't kind of distributed across multiple subroutine interfaces. And so the potential return on investment is that on the CPU, you're probably going to be running out of the memory, accessing memory in these loops, and on the GPU, if you can fit this problem onto the device, then you can benefit from the greater memory bandwidth. So so it is amenable, and the return on investments is kind of the ratio in memory bandwidths between the two devices. So the next step in this GPU enablement process is decide on a code conversion or redesign approach. So in this case, we're going to use directives because it's written Fortran. And the other issue to think about is managed or explicit data movement. And we decided to do explicit data movement because we wanted to get the most possible out of this implementation. So the rest of the GPU enablement process is just kind of a mechanical application of directives. You add directives to a single loop, you verify and correct performance issue, and then you repeat. And so going to kind of step through that, go back to our code example. So just add an OpenACC parallelization directive on this loop that parallelizes the calculations, and then you need to move the data onto the device. So you do a copy in and a copy, as well as a copy for the resulting the results. And so so you've basically done one loop, and so you do that for all the loops you find. And so you can see here that you have GPU offloading for multiple loops. This is a pretty, so what you've done is you've put part of your calculation on the GPU, you've slowed the code down significantly because you're involving all this data movement. So this is the discouraging part, but we'll get to that later. So then you can go ahead and merge the neighboring data regions, and you get a little bit better performance because you're you've minimized some unnecessary data movement. So you just go ahead and repeat this for the rest of the subroutine. And so now I'll solve two calculations of GPU resident. You just repeat, right? This is, so you've done one of the main subroutines, and pretty soon you just push out to the entire time stepping loop. And so this is actually a wonderful time when you finally push all the data movement outside the time stepping loop, because previously you'd very consistently slow down the code, and all of a sudden when you get all the data movement outside, you're rewarded tremendously, because all of a sudden you get to see the fruits of your labor. So all right, so estimating the effort of the GPU enablement, this is another thing that people will ask you. It'll be like, how many years did it take you, or how much FTE effort? And it really kind of depends upon the size of the code. It also depends upon some other characteristics. So is the code GPU ready? And you can actually sort this out fairly quickly by just looking at the loop structure. If it looks like the loops, all the parallelism is at the bottom level, then the code's probably GPU ready. If it's not, this is going to be a bigger effort, because you need to do the conversion so that the code is GPU ready. Another important question is, does the code currently support OpenMP on a CPU? If not, then there's another large effort necessary to support threading-based parallelism. So another one is, how many OpenMP directives are there? If you got a lot of OpenMP directives, you need to add a lot of OpenACC or OpenMP offload directives. So all of these kind of effort can be done ahead of time. The first three, that is. One of the ones that's going to be kind of the wild card is, how many conceptually challenging problems really are there in your code? And it's not possible to determine this a priori. We found that basically you need to push through the work, and then you kind of find them. So what does this look like for the particular application we worked on? There was a lot of OpenMP directives, close to 4,000. So when we the mostly complete port to OpenACC resulted in nearly 5,000 OpenACC directives. So a similar number for the parallel loops, but then there was update directives and data directives that were necessary to control the location of where memory is, whether it's on the device or the GPU device or the CPU. So really a modest increase in the number of directives over the original OpenMP. Again, this is relative to the number of OpenMP directives that you have, and the additional ones are associated with the data movement and allocation. So some of the challenging areas, a lot of duplicate code and directives in CM1. If you're thinking about this for your application, then maybe you don't have as many directives, and that would be a good thing. The other experience that we had was that I talked about the was that a lot of the directives were conceptually trivial, and we showed in a couple of slides ago what a conceptually trivial application of a directive looks like, and so greater than 99% of them were conceptually simple. It involved cutting and pasting. It kind of triggered carpal tunnel syndrome, because you're doing the same thing over and over. But this can be done by students, I think. Hire some undergraduates. Much less than significantly less than 1% of the loop are very challenging. And one of the examples was a fallout subroutine where it iterated over vertical K loops. It requires about 5 rewrites for for the GPU before it was performant. Another example is the min-loc and max-loc operations. They're fairly simple when you think of serial code on how to write it. There's an actual built-in intrinsic in the Fortran language, but they're surprisingly challenging. And so, I went to experts at NVIDIA and I asked them how to do that. And then they started arguing about it. And they're like, oh, we think that's gonna be in the compiler, in 4 months from now. And so this was surprisingly challenging. So you will find these loops and structures that require some intellectual thought. But at least in our application, there is a very, very small number of them. Okay, so frequent systematic correctness testing is critical. It's much harder to regain correctness if you've lost it rather than to maintain it. Don't lose faith prematurely. So, as I tended to hint at perhaps earlier, it can be kind of discouraging as you GPUize your code and it keeps getting slower and slower and slower. But the true potential is really apparent only once all the calculations are, maybe I should say most of the calculations are GPU resident. So if you get discouraged prematurely, then you don't get to that reward. So this is kind of the result of this work of the GPU enablement was we were awarded an accelerated scientific discovery allocation. This was on the new system that will be installed at NCAR this upcoming year. And we're looking at turbulence in the hurricane boundary layer. It was approximately 60,000 GPU hours and will generate 72 terabytes of data. The configuration was, I mentioned before, 2,000 points in each of the horizontal and 1,000 in the vertical, and we'll be targeting 64 to 128 NVIDIA GPUs. And the performance comparison that we got, this is the magic number that people frequently quote. So we compared 4 NVIDIA V100 GPUs to 4 Cheyenne CPU nodes. These are roughly contemporary, these are old hardware on both accounts, but they're roughly contemporary. And so we saw a 4.4 reduction in execution time on the 4 GPUs versus the 4 Cheyenne CPU nodes. So some conclusions, we described the entire GPU enablement process. Again, I think the decisions that go into whether you make the investment is critical, and also kind of identifying a interesting and complementary science problem. It really requires a diverse set of skill sets. You can't do this without the domain scientists. You need people that are interested in computer architecture and understand how it interacts with the software design, software engineers to plan a systematic refactoring, and it's also very beneficial to have students to perform the code conversion. Though this project actually didn't involve any students, but it is very possible and useful to have the students. And of course, significant acceleration is possible for a GPU-based code. That's it. Do you have any questions?
Thank you very much, David. Let's see. I don't see any questions on Slido, but then maybe, oh yeah, I just saw one. Awesome. Thank you, Eric. 2. Okay, so the first one is from Eric. You said students could do 99% of the loops, but 1% were challenging. Could the students identify the challenging loops and be able to pass them off to others to work on? Or would that just fall out from testing?
I think it would fall out from testing. The other thing that they would do is they would do something, like a simple treatment of the loop. And then when you do you would either get correctness issues that are from that loop, or it would show up as a huge performance problem. So you'd have this, the way it looked, this tiny little loop was consuming 40% of the time. So.
All right, thank you, Eric. From Tim, did you consider using OpenMP offloading instead of OpenACC?
No. So at the time that we started this project, we talked to the, people that were familiar with both, and they were warning us away from OpenMP offloading at that time. So we went with OpenACC. Very recently, we've discovered and observed that OpenMP offloading is very competitive, and so if I was starting this today, I would do OpenMP offloading.
All right, thank you very much. Thank you, Tim. And from John, great talk, which
Thank you.
I concur. Thank you very much. Any other questions? All right, well, thank you very much. And then, thank you very much, John. And let's see. So now we go on to our next talk. That's going to be Timothy Brown. And let's see. So I guess we're going to wait for Timothy to put his talk on. But Timothy is a principal solutions architect from Compute and HPC at Amazon Web Services. And the title of his talk is Scaling NWP Workloads on AWS to Achieve Your Research Goals. And I think we're ready. So go ahead. Thank you. All right, all good?
Okay, can everybody hear me?
Yes.
Perfect. I'd like to actually introduce Sean Smith. These slides are going automatically. There we go. Sean, are you on? Sounds like he's not. I just Slack him to see if he's available. We were going to split this talk into two. Sean Smith was going to give the first part, which is really an introduction to AWS and AWS techniques. And then I was going to do the second half to drive it through to for an example. Maybe I'll give him a couple more minutes because we're 5 minutes ahead of 1:30. See if he shows up.
Yeah, we are a little bit ahead. Actually, we're 6 minutes ahead. So. Timothy, about Sean Smith, just a little brief note. Is he also part of the same place, HPC?
Yes.
Okay, just as
yes. Yes, so Sean is a senior solutions architect at AWS as well. And
okay. So go ahead.
Go ahead.
Well, I was just going to say that I think in all fairness, we should wait the 5 minutes for him to be here. So we'll wait until the 1:30 time.
Okay.
If that works for you, of course.
Yes, definitely works for me.
Okay, sounds good. It's a little bit of a stretch. It's always good for everybody.
Hi, Tim.
Hi, Sean.
Right.
We're actually going to wait until 1:30 before we kick it off, Sean.
Okay.
No, I mean, if you guys want, you can go ahead. I was just going to say until 1:30 in case Sean was not able to come before that. But if you guys, you can go ahead. It's up to you.
Yeah, we can do it right now.
All right. Okay. So thank you very much. And again, Timothy Brown and Sean Smith. with scaling NWP workloads on AWS to achieve your research goals. Thank you.
All right. Hello, everyone. My name's Sean Smith. I'm a HPC specialist at AWS, and I'm joined today by Tim. Want to give your background, Tim?
I have actually.
Oh, okay.
That's okay.
Sorry. Okay. Let's go to the next slide. So today we'll give you a little overview of what we call HPC at Amazon. We'll show you an example of how we orchestrate that with something called Parallel Cluster Manager. We will then go on to talk about some of the weather applications and give some performance results. And if we have time at the end, we've got a short demo. All right, so when we think about HPC, we've got three main components. We've got compute, networking, and storage. So first, as a user, we connect in. So we're going to connect either via the DCV or SSM connection. So the difference between these two, and I guess a third way would be SSH. The difference between these two is one gives you a graphical desktop. So you can think of that as like your remote desktop. It uses a software called DCV, which streams the pixels. And so it's low latency and provides a good user experience. And then that connects you into a head node. So that head node runs a job queue. And the way we orchestrate that is via Slurm. So Parallel Cluster, you can think of it as a managed Slurm service. So it hooks into Slurm's power saving plugins and provides auto scaling, as well as hooks up the storage. So we've got a managed FSX Luster system, and that oftentimes we see users using that as like a cache to an S3 bucket. So S3 will be the long-term storage. You can think about storing your models in S3 and then using FSX Luster as the long-term cache. And then from there, we've got compute. So you can have different queues to specify different compute. So we've got G4, which is our GPU-based instances, HPC 6A, which we'll talk about in the next slide, which is our HPC-focused AMD EPYC Milan instances, as well as a high memory queue for 16 gigs per core memory ratio. So that's kind of how the architecture works. And the key here is that Parallel Cluster creates all of this, and it makes it easy to interact with, and it can be spun up easily. So let's see, going to the next slide. So if you've taken a look at the AWS console, you'll see there's like 100 different instance types, and it can be kind of confusing which one to use, especially if you're used to a managed cluster where you only have a few compute options. So I want to call out two different instance types that we'll show later when we show some of the NWP benchmarks. So the first one is the HPC 6A 48x large. One trick that I often tell users about is that the 48 actually just stands for the number of physical cores per socket. And most of our machines are 2-socket machines. So the trick to figure out the number of physical cores is take the number at the end and multiply it by 2. So we've got 96 physical cores, 4 gigs of memory per core, and then this has 100 gig networking with our low latency interconnect. It's called Elastic Fabric Adapter, EFA for short. The next instance that's relevant is the Ice Lake instances. So this is the latest Intel generation. It's got 64 physical cores and 256 gigs. And then it's also got EFA enabled. We put some pricing down at the bottom because I think you'll see that we've priced the HPC 6A to be the best price performance instance out of the selection. And so yeah, it's priced at 3 cents per core hour in the Ohio region. And we've also launched it in 2 different regions for the start. So Ohio and our GovCloud, which is like ITAR restricted workloads. And the reason for that is we've got deep pools in those regions, and we have customers that are running tens of thousands of cores on a daily basis in an on-demand manner, spinning up for just a few hours, completing their workload, and then spinning them down. Okay. Next slide. So when we think about HPC, networking is one of the biggest bottlenecks typically. And that's why we built this elastic fabric adapter. So it does OS bypass. It's built into the libfabric layer. So it works with all the most common MPI implementations. So Intel, MPI, OpenMPI, and MPitch. And then it works a little bit differently than InfiniBand or other interconnects in the sense that it does multiple paths. So we created an algorithm called scalable, reliable datagrams. And so it sends these datagrams over the Ethernet layer, and it makes it a lot more fault tolerant and scalable than an island of maybe InfiniBand nodes. And it'll go up to 400 gigs of networking bandwidth. And so what we see in practice, we showed there's a scaling chart of an EFA enabled instance, so the HPC 6A on the right. And that'll allow you to get up to 10, 20, 30,000 cores with very good efficiency. All right, next slide. So to bring all this together, we created a tool called Parallel Cluster Manager. So this is a UI to create these clusters and manage them. So it'll give you access to the shell as well as DCV. So you get a nice convenient button there that can connect in via the web browser. Fun fact, you can actually do this on your phone, create a cluster, submit a job from the web UI, all from mobile. It gives you the ability to configure these clusters, and it's not just the when we say configuring a cluster, you might think of that as like configuring the Slurm queues. So you're specifying hardware, you're specifying where these instances should launch. So we have the notion of a availability zone, and then at an even more granular level of placement group, and that's going to get you placed on the same spine. So that will give you the lowest latency communication. As well as when you're done, you can just stop your cluster. This will preserve all the data, and it allows you to resume easily. You can save the hardware configuration of that cluster. And so it's a convenient way to do some research, pause, and then come back later when you need it without spending any more setup time. So Tim, on to you.
Thanks, Sean. So what is really happening behind that web interface is essentially this YAML file that you see on the left with some more paragraphs around it. At AWS with Parallel Cluster, we are using Slurm as a built-in scheduler. And a point to note here is that we've defined 0 minimum nodes, which means by default, no nodes are running. And then you can specify a max count of 200 nodes, for example, in this example. And then what we achieve is by using Slurm's power management is that those nodes are actually idle and turned off. That's what the little tilde is about there, which means you don't get charged for these nodes at all if you're not running a job on them. So installing software is kind of the bane of most sysadmins' life and everything. But there's three main common ways that you can do this. One is through a custom Amazon machine image via Packer. So this is really just almost like a container, but even more. It's the whole machine image. It's like an ISO. And then the other one is package managers, for example, SPAC and Easy Build. And then the third is the really old traditional way of doing it by hand, which is normally always error prone, and you can normally never reproduce what you built. I prefer to use SPAC. And so in this example today, I'm going to run you through using SPAC. And SPAC was from Lawrence Livermore, from Todd Gamblin originally. We've had a couple of talks earlier in the week that address SPAC. So this here is how we suggest you just install it. You set a SPAC root, clone the repo, set a couple of environment variables, and source the SPAC setup environment. So then you'll be able to use SPAC as a command. With Parallel Cluster, there are actually some external packages already installed in the Parallel Cluster AMI. So we want to tell SPAC about those packages. The most important three are libfabric, PMIX, and Slurm, so that you can basically tell SPAC that you're using Slurm with PMIX and that you want to use libfabric that comes pre-installed instead of trying to install its own version. So typically we define these in a packages.yaml file within a SPAC directory. So weather models that have been run on AWS, everybody always shows the WRF ARW CONUS benchmark. So that one's definitely been done a lot of times. MPass atmospheres being run there too, UFS, FV3, GFS, the unified model from UK Met, Harmony from the DMI, and ICON from IMS, the Israeli Met Services. So today, I'm going to be focusing on UFS. So specifically, this is how I build UFS on AWS. It's really a mouthful if you are unfamiliar with SPAC. So I'll just walk you through the arguments and flags to it. First one, install, says what it does. You're installing a package. The -- reuse really tells SPAC to try a little bit harder to reuse already installed dependencies instead of rebuilding the whole DAG for you. The -J12 is exactly the same as make. It does a parallel build. The UFS weather model, that is the package that we are trying to install. And then the % after that is telling it what compiler. So %Intel says we want to use the Intel compiler, which is ICC and iFort. The hat tells it what dependencies you want in there, so that you're saying, okay, build the UFS weather model with the Intel compiler, but also use the Intel One API MPI. And then the plus on the end of that is to tell what features you want turned on in the Intel One API MPI. And we want to tell it to use an external libfabric, which is what we have defined earlier in the packages.yaml file. You can quickly get yourself very confused in using SPAC. I feel it has a very steep learning curve, but once you get there, it is actually wonderful to use, in my opinion. So then running the UFS weather model, there's a couple of gotchas that you got to watch out for. And I'm just highlighting them here. This is your typical batch script for Slurm. So you've got your SBatch directives at the top, like job name, where to put your output, how many nodes to run on, how many tasks or MPI ranks per node. And then the first gotcha is that you've got to export the MPI OFI library internal to be 0 to turn it off before you load the MPI library. Once you load that, then we just do a SPAC load for the MPI and the UFS. And then we do a module load because the libfabric provided by Parallel Cluster comes in a module file. And then set stack size, for example, then turn on MPI debug so that you can get some information about MPI. I like to do this to guarantee that I can see that I am using EFA. And then we tell the MPI library to use the OFI, so the libfabrics, and then we say the libfabric provider is EFA. And that is the main point that really is a stumbling block for the first time you get onto AWS, is if you don't set your OFI provider to be EFA, you end up using TCP, and then you sit there scratching your head wondering why everything goes really slow, and you start to think that AWS really can't do HPC. And then we pin our domains to be OpenMP, and then OpenKMP thread affinity to be compact, and the number of threads to be 6 in this example. Then we just execute, so the UFS weather model, which leads me into performance graphs. So this is UFS version 2 doing a C768. 768 run, which is about 13 kilometers and a 24-hour forecast. So Sean pointed out earlier, we've got the C5N, which is our previous generation of Intel, and the C6I, and then followed by the HPC 6A. HPC 6A is the AMD Milan chip, and here we've scaled out to 144 instances. We see that the scaling does tend to peter off and bottom out really when you get out to that such a large instance. And then the simulation speed, which is really considered kind of the forecast length divided by the simulation time. So, 24-hour forecast divided by how long it took to get there. We can see a massive speed up with HPC 6A over our C5N instances, followed by scaling costs. So one always has in the back of your mind, how much did this really cost me? Since AWS and all cloud providers, you really have to front up with your credit card at the beginning of anything. So really always keep in mind the actual cost. And once again, HPC 6A is about 80% lower than C5N. So really keep that in the back of your mind as well. Finally, the price performance. So what this price performance is a cost to the result divided by the simulation speed. So really showing how good HPC 6A in the sense of that you really want this price performance line to be fairly linear and low. Finally, we have actually put together a weather workshop that covers 3 main North American models, for example, WRF, MPAS-A, and FV3 GFS. It is designed to be a self-paced guided tour of yourself that you can undertake yourself, sorry. That's the URL there for you, and that's it. Over to questions, or to Sean if you want to do a live demo of.
Excellent. Yeah, let's pause for questions, and then I can do a demo. I saw there was one question in the chat that was asking about the UI for Parallel Cluster. So yes, Parallel Cluster Manager is the UI, and you can find it. I put a GitHub link in the chat that will allow you to install it. Tim, you want to take the next question?
Sure. I've got to try and find it.
So
can you read it?
Yeah. So do you need to see all the MPI variables explicitly if you are loading the Intel MPI module?
So you definitely need to set the first one to say use, do not use your Intel MPI fabric, to use the external one. And then let me confirm. I tend to always set them no matter what, so that I know what I'm doing. But that's just me. I personally would suggest doing that as well. And I just confirmed that, yes, you do actually need to set them. I'm looking at the module file right now. So that is a yes, you do have to set them.
All right. Next question. Thank you, Christina. So next question is from David. At what point does SPAC build install software? Does it create an AMI or does it wait until the cluster starts from the parallel cluster base image?
So what I have shown you today is installing it on a parallel cluster base image. I tend to do that rather than creating an army, because I tend to spin up and tear down clusters not that frequently. So my code base doesn't change that often. And so therefore, yeah, I'm lazy in that sense, if I want to be blunt, that I don't want to really invest in, using Packer to create a whole thing. It is definitely possible to use Packer to, when you build the AMI, to install SPAC and therefore install all your packages into your AMI. I tend to just do the SPAC build and then let it run, let the packages live on OpenZFS, and then I have a mount that on all my compute nodes as well as my Lustre file system.
Yeah, it should be, I think another really cool thing you can do is so install all those SPAC packages on your Lustre file system and back that up to S3, and then keep the SPAC packages in S3 so they're persisted, and that kind of becomes your /apps directory, and you can just attach that to any newly created clusters, and you're paying very little in the meantime because it's just that S3 storage.
All right. Thank you very much, Timothy and Shen. Are there any other questions?
I can do a demo really quick.
We have time.
Okay. Sure. Okay, let me know if you can see my screen. It should be showing the web browser.
Yeah, you can see it.
Okay. So what I'm showing here is the parallel cluster manager that we were talking about. So this is a pre-created cluster. You can also create one. We talked about the weather workshop. So that's here, and it goes through the different steps. So it goes through the installation of the web UI, creating the cluster, and then we've got steps for WRF, MPass, and UFS. And these are actually all backed by a SPAC binary cache that we maintain for these applications. So you can install them in like literally 5 minutes after you get the cluster up, which is really cool. So let's see. Going back to the manager interface, to get started with the cluster. So jump to the create the cluster. We've got a template here. So if you just click download template, this will give you what you need. So you can save this. You can't see it, but it's saving it in my downloads. Okay, and then if I jump back here, I can click create cluster. I'll call this cluster, select template. In the next step, it will ask me to upload that template. You won't be able to see it because it's Zoom just shows the web browser. And then it's going to pre-fill all the information in. So the region, scheduler, operating system. I'm using Amazon Linux, but you can use Ubuntu or CentOS. And then it'll have me select all of the things that are specific to my account that aren't in that template. So like the VPC, the subnets. So in the workshop, we advise you to use US East 2B. This is where the HPC 6A instances are. Key pair, you can select one or you can say none. If you select none, you can connect via the web console. We go next. So this section is going to set up our Lustre file system. So we're going to mount it at /shared. It's persistent 1. We can set the per unit storage throughput. So this is the megabits per second per terabyte provisioned. And we're just going to provision 1200 gigabytes. And then this is where if you had an S3 bucket, let's say with your SPAC packages, you could put it here. And then we're going to turn on file system compression because that actually decreases latency and increases bandwidth, which seems hard to believe, but it works really well. Going on to the next step. So this is where we configure our compute queues. Instance type selection. We're going to select the HPC 6A instances. There's a lot of instances here, but it tells you the vCPUs in memory or cores for the HPC 6A. So you can select from GPU, CPU. So this is our 96 core instance. And when we select that, we're going to want to enable EFA. This dynamic nodes, so this sets, you can think of this as like the queue limit. So how many nodes can you scale up to? And then static nodes, this is how many do you want running at any given time, even if there's no job submitted. So highly advise you keep this at 0 unless you have like a steady state workload or you've purchased reserved instances and want those instances available immediately. So then we go next, it's going to give us a review screen. So on the screen, we can hit dry run. It's going to make an API request to validate this template. And this template is, you can think of this as similar to a CloudFormation template. It's your cluster configuration. It's your infrastructure as code. It defines the Slurm queue setting, and it allows you to reproduce the same cluster in the future. Then you hit create. So it's going to go off and create that cluster. Once it does that, it will kick us back to the review screen. Okay, so now it's creating. It allows us to see the events down at the bottom here of the different resources. If you've used CloudFormation before, you might recognize these as just CloudFormation events. So then once our cluster is created, it takes about 10 to 15 minutes, depending on the file system is typically what takes the longest. Once it's created, it'll give you this details pane. So you can see it's running, gives you the ability to connect to it. This uses EC2 Instance Connect. So it actually like creates a temporary key pair, syncs it with the cluster, and allows you to SSH in with that. So key pairless SSH. As well as we have this shell button. So if I click on this, it will connect me into the head node. Ready? While that's loading, I'll go over some of the other options here. So you can see the instances that are running. In this case, I only have my head node running. And if you stop the cluster, you can also stop the head node. You can see the storage. So this is our Lustre file system mounted at /shared job scheduling. So this allows you to submit and view the jobs that are running. I don't have any running jobs in the cluster right now, but if they were, I could cancel them from here. And I can also submit a job. One of the nice things about this is it gives you the ability to see what a job will cost before you submit it. So let's say I do a 2-node job. So that'll give me 192 cores. So a small job. and I know it's going to run for an hour and a half. So I can estimate the cost on that. It'll tell me it costs $8.64. And that just takes the on-demand price, and it'll give you the how it got that number down below. Okay, going back here. All right, cool. So we've loaded in. Once you're on the console, you'll be able to see and use standard Slurm commands, so we can see our instances are idle tilde, meaning they're not running. And we go df-h, you can see that we've got our shared file system attached at /shared. And in that we have our SPAC packages loaded. So if I do SPAC find, that'll show me, okay, I've got the Intel 1 API compilers, as well as WARF and UFS, and the dependencies of that, and also MPass. And to get this exact same setup, like I said earlier, you can go through this workshop. It'll have you install SPAC, as well as add our build cache. So we've got an S3 bucket where we keep those packages up to date for this architecture. And then it'll have you go through the compiler install. Yeah, I'm gonna pause here. That's the end of my demo, but I'd be happy to take more questions if there are them.
All right, thank you very much. And we have around 2 minutes before our break, so any more questions? Right, so then I guess no more questions. So thank you again, Timothy and Shan. And we are going to have a break now, and we're going to get back at 2:20. So, and that's going to be the last stretch of our conference. So enjoy your break and see you soon at 2:20. All right, welcome back to the final stretch of our Improving Scientific Software Conference. And our next presenter is Dr. Jonathan Edelen. So Dr. Jonathan Edelen is an accelerator scientist at Radiosoft, and his presentation title is Implicit Optimization of Accelerator Beamlines with Machine Learning. Thank you very much, Jonathan.
Thank you for the introduction, and thank you for the opportunity to share some of my work here at this this conference. And apologies that the slide title doesn't match the title in the description, but that is the subject of the talk. Yeah, so hi, my name is Jonathan. My background is largely in particle accelerator technology, and more recently I've been working machine learning applications for accelerator technology, and I understand that there's quite a lot of work in machine learning for weather modeling and other related things. So I think that even though the applications are a bit different, there may be something here that is of interest, and I hope that there's some, just to give you an idea of kind of some of the stuff we're working on, and hopefully there's some cool takeaways. So first off, I just wanted to highlight kind of a broad scope of different projects that we're working on involving machine learning at Radiosoft. Radiosoft's a software company based in Boulder. We're largely a computational physics company, but we also have a pretty strong machine learning program, and then we also build user interfaces for scientific computing codes and do a lot of high performance computing on GPU servers and on CPU servers, multi-core processing, things like that, largely for accelerator technology, but in some cases we do focus on other technologies. But one of our flagship products is creating graphical interfaces for sort of legacy scientific computing codes. And on the machine learning side, we are interested in quite a range of applications. So here are a few examples. On the accelerator technology side, we're interested in diagnostics and in tuning. So this is, from a diagnostic standpoint, it's trying to infer more information or additional information from diagnostic output that you can't necessarily get without extensive post-processing. So here we're looking at using variational autoencoders to interpret beam position monitor data. And essentially, in a large ring, you have, you know, maybe dozens of these beam position monitors around the ring. And if you look at all of them in aggregate, you can learn a lot of information about what's going on in the accelerator. But that generally requires a bit of post-processing. So we're hoping to build tools using variational autoencoders to sort of synthesize that information down and provide diagnostics for operators that are useful for tuning on the fly that don't require a lot of post-processing. Tuning is, of course, always a challenge in running particle accelerators, and making sure the beam is delivering the right parameters for the end users, and just making sure that the machine is running correctly. We're not getting a lot of beam loss or things like that that can be problematic. So machine learning based tuning is a very popular field right now, and there's a lot of interesting work going on in both at Radiasoft and sort of in accelerators at large. We've also got some projects focused on the user side. So we have some collaborations with the neutron science community to improve sample alignment. So this is sort of more classical image recognition problem. And then also on the X-ray user side, predicting beam information from scalar parameters. So if you can't actually measure the beam usually that you're using to image a sample in an X-ray beamline. So at least when the sample is installed anyway. So the idea here is to infer the beam information from all the other diagnostics that are available, and use a machine learning model to predict what the beam is looking like, so that you can get a representation of what kind of image you're going to get from your diagnostic. And then also we're interested in laser technology, and we've been using machine learning to help with sort of automatic alignment of high power lasers this is mainly for plasma, laser plasma based experiments at some of the national labs. Okay, so when thinking about tuning or thinking about machine learning for accelerators, usually break the scope down into a couple of different topic areas. We talk about accelerator R&D, which is one of the main uses for accelerators on like the accelerator science side, is trying to improve the machines, either through machine development time or specialized R&D facilities. And then of course the users are the prime customer for particle accelerators. So making sure that the beam time to experimentalists is optimal. And then also minimizing downtime, whether that's scheduled maintenance or unscheduled maintenance, trying to make sure that unscheduled maintenance is not occurring and that it's more of a scheduled maintenance thing. So if we can do predictive fault detection, that's a popular area of interest for machine learning and accelerators. And I think there's a lot of interesting work going on there. And that kind of gets classified into these three sort of topic areas specifically for machine learning. So you have the accelerator applications, and then there's the machine learning, like what kinds of specific things are you using. For tuning, we look at inverse models, and that's kind of what I'm going to talk about today. And then also just direct neural network based controllers for optimization and control. And then another thing is using neural networks and machine learning algorithms for surrogate modeling. And this is basically trying to take a high performance computing code that maybe it's running at NERSC or on another cluster, or maybe it's running on a GPU. And those things aren't necessarily available to operators in the control room. So what you might want to do is run lots of models on these high performance computing resources, and then train a neural network surrogate model to give you a pretty good representation of that in the control room, and use that to assist with tuning and assist with operations. And there's actually a couple of groups that have been deploying these at Stanford, at SLAC, for example. They have a surrogate model system that they're building for the electron accelerator there, and they're sort of in the process of integrating that into the operations of the machine. And then, of course, anomaly detection is always an interesting area for accelerator applications, trying to make sure that the beam is behaving correctly, and then also, like I was saying, trying to predict faults before they occur, so that we don't run into problems with the machine, and we can fix parts before they break, type of a thing, and replace power supplies, things like that, so that we don't have unexpected downtime. So the focus of this, that's kind of the broad overview of the landscape of machine learning, at Radiasoft. And now I'm going to kind of drill down into what we're doing specifically in how we're applying inverse models to tuning. So from a parameter standpoint, or from just like an intuitive standpoint, the most easiest conceptual way to think about using inverse models for accelerator tuning is a direct inverse model for tuning. And what I mean by that is you have, let's say you have a set of beam position monitors that are reading the beam position throughout the ring, and you have a set of correctors, and those are basically a bunch of magnets that change the position of the beam in the ring. And you can learn this relationship between the BPMs and the correctors using a neural network. And the idea is that once you've learned sort of the inverse problem, which is predict correctors from BPMs, you can supply the neural network with a desired trajectory, and then it'll just spit out the corrector settings that you need to apply to get this beam orbit or this beam trajectory, in the ring. And that's a very intuitive problem, and this is one of the classic examples that people start with when they're considering inverse models for tuning and accelerators, is this BPM to corrector relationship. And then also you can think of this as using this as a prior for an optimization algorithm. So you can have those predicted corrector settings and use this as an initial starting point for some kind of optimization that's using the correctors to minimize the trajectory, the difference between the current trajectory and the desired trajectory, basically give you the expected experimental setup for the accelerator. So both of these are pretty classic use cases for inverse models. And we've done a little bit of this at the Brookhaven National Lab. And this is an overview of that accelerator. So for the application that I'm going to talk about here is for this transfer line from the alternating gradient synchrotron, which is the AGS. That's this ring down here. And this ring is responsible for accelerating ions up to a certain energy. Then there's a transfer line that takes them over to RIC, which is the relativistic heavy ion collider. And then once you get into RIC, you have there's both the gold and the yellow and the blue lines, which are the two counter-circulating beam lines, and then there's the collider interaction points. But this transfer line between them is kind of a complicated transfer line. It's 600 meters long. It has quite a few different magnets, and it's really important to not only optimize the beam orbit through the transfer line, but also optimize the beam envelope through the transfer line. So this bottom plot is showing basically the beam envelope through the transfer line for the nominal trajectory, which is the solid line, and for a perturbed trajectory, which is the dashed line. And even for a relatively small perturbation in energy, which is gamma here, first of all, the losses drop significantly, and also the beam envelope is now no longer well matched. And the reason why there's a lot of losses is because there's apertures in there, and unless the optics or the beam envelope is tuned very well, the beam's going to hit the aperture, and then it's going to you'll have losses, and you won't get good transmission to the collider. So when you think about bringing this back to inverse models, the sort of initial thing is, okay, well, can we train a neural network to learn how to adjust the optics of the beam line using the diagnostics that we have, and just say we'll be able to correct for this the same way we do for BPMs. And the problem that you run into is that there's basically a degenerate solution of optical settings that you can make that will give you you can't tell the difference between measured changes in the beam position and changes in quadrupoles directly. Quadrupoles are what's used to tune the optics of the transfer line. So because you have all these degeneracies, you basically can't train the inverse model. I mean, there's things you can do. You can try to work around it. There's a number of efforts sort of focused on how you could get around the degenerate solution problem. But what I'm interested in here is using the fact that there's a relationship between when the beam goes through a quadrupole and the quadrupole is excited incorrectly, that shows up in the relationship between the BPMs and the correctors. And you don't necessarily need to explicitly learn this relationship between the BPMs and the optics. You can just look at the BPMs and the correctors, and from that you can retune the optics to be correct. And I'll get into how exactly that works in the next few slides. And this slide's probably a little out of order, but this is just an example of using machine learning for orbit correction. So we have the beam comes in at an offset, and you tell the inverse model, I don't want the beam to be offset. And then the inverse model spits out a set of correctors that realigns the beam. And this is just a fairly simple example of that on that transfer line. And then this is the bottom plot is doing that same thing, but now iteratively optimizing the correctors to retune the trajectory. All right, so inverse models now for diagnostics and for tuning. So you start out by using it as a diagnostic, and then from there we sort of consider how we would use it for tuning, because they're kind of the same thing in a sense. The idea is, how can we understand what are causing like optical aberrations in the beamline, and how can we infer that from the limited diagnostics that we have just from the BPMs and the correctors. And the idea here is that you have a set of measured BPM measurements, and you take those into the neural network and you predict the correctors. And the correctors are, you have actual corrector settings in the beamline in the accelerator control room. They're sort of real parameters that you can see. This is the corrector. And then you can compare the predicted corrector settings to the actual corrector settings. And when you do that, that gives you an idea of, you're basically saying, hey, the model is not agreeing with what the machine is saying. And you can use this as potentially as a diagnostic to find other errors in the machine, or you can use this for tuning. So if, for example, one of the other magnets is mistuned or misaligned, that would show up as there would be a signature of that in this model, because the BPM corrector relationship would now no longer be consistent with the measurements you're getting from the BPMs and the correctors that you're seeing as actual settings. So to sort of validate this, or to try this in a very, very simple problem, we consider basically the simplest possible beamline. It's an overdetermined system, and this is just to get a feel for whether or not this is going to work. And this problem, I mean, you can almost solve it analytically, and it should work. But this is kind of like first gut check before moving on to applying it to a more sophisticated system like the transfer line that I was discussing. So here we have a very simple beamline that has 2 quadrupoles. Those are the red magnets, 2 correctors, which are in black, and then 4 BPMs. And the goal here is to take BPM measurements and predict these correctors, which are called kickers. They're kick in both X and Y, the 2 transverse planes, and say, from the BPM measurements, let's predict the correctors, and then we're going to vary the quadrupole strengths. And as we vary the quadrupole strengths, we're going to look at the error in the model prediction for the correctors compared to the actuals. And we're going to see if there's well-defined minima, or if we could actually use this for tuning, or at least for, if nothing else, could we detect a quadrupole error by looking at the relationship between the BPMs and the correctors. So the bottom left here, this is showing the output of the neural network, the predicted corrector setting versus the validation corrector setting. For just the standard no quadrupole errors, quadrupoles are set to their nominal value, and then just to make sure the model is well trained. And then on the right, we're looking at the model error for each of the correctors as we scan the quadrupoles, and we scan the 2 quadrupoles independently on the top, and on the bottom we scan them together. So the first thing to note is that as you scan the quadrupoles, you do get a very nice correlated error in the model. Excuse me. There's a nice correlated error in the model that has a global minimum at 0 error, which is the sort of nominal excitation. So that's very encouraging that for both the cases of looking at the error in quadrupole 1 or the error in quadrupole 2, the model error, so that's the difference between the predicted corrector setting and the actual corrector setting. Remember, we have actual corrector settings because we have the correctors for the machine, and that correlates very well as we change the quadrupole excitation. And on the bottom plot, this is just showing the 2-dimensional version of the top plots, which highlights that there's a fairly broad minimum, but there is a nice minimum around 0 error in both excitations, which is encouraging, because what we really want to do is not just use this for diagnostics, but also use it for tuning. So we want an optimizer to be able to adjust the quadrupoles to minimize the model error, so that we can get back to a specific lattice configuration, and we can retune to adjust for errors in the beam. So the next thing is to run this actually on a model of the AGS direct transfer line. So this is the beamline that I was mentioning before, and it's the 600-meter beamline. And to do this, we generate two different data sets. So this is all done, we're in the process of running this on the machine, but right now all of our work has been done using what's called the MADX model, and MADX is a particle tracking code that basically simulates the beamline. And the first thing to do is just to train the neural network model, and the neural network model is trained by all the quadrupoles are set to their design values, and then we randomly vary the correctors and observe the BPMs, and then we use that data to train the neural networks. And then the testing data is generated in the same way. However, now we systematically vary all the quadrupoles one at a time between plus or minus 20% excitation, and also randomly vary the correctors and randomly vary the BPMs to see if we can detect the errors in the quadrupoles by taking this test data and applying it to the model as trained on the training /validation data. So the first, and this is an example of that. So we took the data and we applied it to the neural networks. And here we're looking at a case where there's no quadruple errors. There's a single quadruple error of minus 20% excitation, and then there's a quadruple error of plus 20% excitation. So inside the transfer line, there's about 19 quadruples. We picked one of them and varied its excitation, and then took that test data and ran it through the neural network to see if there's the error in the predicted corrector setting shows up. And here on the right hand side, this plot is showing the predicted corrector setting versus the ground truth corrector setting for the dozen correctors that are in the ATR line. And the cases where the black, the blue, and the red all line up, that means that we didn't detect anything, or at least there's no signature of an error there. And then the cases where you start to see a spread in the red prediction, a spread in the blue prediction, that indicates that there's something that has changed about the sort of underlying system that is detected by this model. And we can see that very clearly in both these three correctors here, not the first three, but these three correctors here. And a little bit here in this corrector, but not so much. And then as we move down the transfer line, we don't really see any clear signature anymore. And that's kind of expected. I mean, you're gonna see the biggest perturbations at quadrupoles that are located near the BPMs and correctors that you're using to detect the errors. So then the next thing is to sort of understand the sensitivity of each quadrupole with changes in the sensitivity in kicker errors with changes in quadrupoles. This is kind of just, is there a sensitivity matrix? Can we use this matrix as a diagnostic, and just to understand how the model will vary as you vary these quadrupoles independently. So this is just looking at a mean squared error essentially over a bunch of different data points that are collected for each case where you vary each quadrupole independently, and just looking at the sensitivity of those quadrupoles, the sensitivity of the model of the kicker errors to sensitivities in the quadrupoles. So this is, the idea here is if this, visually speaking, if you look at this plot and you see sort of a bunch of different excitations along the horizontal axis, so like looking at, or sorry, the vertical, if you're looking at like where do these quadrupoles show up in the kickers, then we want to be able to distinguish between quadrupoles. So if we see a lot of the same types of patterns, then they might not be useful as a diagnostic, and we would have problems sort of differentiating between, let's say, an error in quadrupole UBQ8 or UQ8 and UQ12. So there's a couple of them that are kind of similar, where we might have problems distinguishing between them, but from a sort of visually, this is encouraging that there's not like a lot of the same information showing up. So there are some differences in the error signatures as you vary different quadrupoles. So how can we use this for tuning? And that's kind of the next step. And the thing is let's look at basically look at the model loss as we vary the quadrupoles independently. So before we were just looking at kind of, okay, what do the signatures look like as you randomly vary correctors? Now let's just keep all the correctors stationary, and we'll vary one quadrupole and look at the model loss essentially for test data as we vary that quadrupole. And this is an example of what that looks like. And for most of the quadrupoles, as you vary them, you get nice minima. The minima is not always around 1, which is a little bit discouraging, because really a 1 is essentially correct excitation, and then plus minus 1.8, 1.2 is basically plus minus 20% excitation. And then there's one quad UQ6, which we're not detecting at all. So essentially we can't use this model to identify errors in that quadrupole, but that's okay. I mean, if we can identify errors in most of the other quadrupoles, that's actually quite encouraging, because it's pretty time consuming to actually go through and test all the different optical components of the beamline. So a quick diagnostic is pretty helpful. So this is encouraging, but it's not the end of the story. So the next thing we said is, what if we use an ensemble? And because we really need this to be unsupervised, we can't actually, every time we do this, check to make sure that we know the quadruple excitation, and we're trying to predict quadruple excitation errors without knowing about them. So how do we go about doing that? If we're just training on data with no excitation errors, well, what if we did an ensemble of models, and then we looked at the ensemble prediction and see how well that does at identifying quadruple errors. So this is the output of the ensemble. So we trained 23 different models, and the bottom plot here is just showing the final loss on the validation and training data for the models. So the models aren't really overfitting. And the right plot is showing that quadrupole sensitivity as you scan the loss for each one of the models as you scan the quadrupole, and what that looks like on a model by model basis. And there's definitely quads where it agrees very well. The models are all kind of consistent. And then there's some quads where the model doesn't really agree very well, or it tends to have a harder time differentiating between or identifying the minimum in that error. But if you look at the sort of on the actual ensemble calculation, which would be maybe you take the mean or the median of the ensemble output as you vary the quadrupole strength, in general, we're getting a nice minimum around 1 for all the cases where we can detect an error. Obviously, again, UQ6, we're not detecting that one at all. But for some of these up here, like UQ2, it's instead of being shifted slightly, the ensemble prediction is now centered fairly nicely around 1, even though it's like a pretty shallow, a shallow curve. So it will probably give us some trouble with optimization, but it is encouraging that the ensemble prediction is pretty well centered around 1, which is good. And this is just showing the ensemble output plus 1 standard deviation. So this kind of gives an idea of how well the ensemble agrees and how much confidence we're going to have in that prediction, which would be useful. So if we use this as a diagnostic, the diagnostic can then use this ensemble prediction to say, we think this is a good or bad prediction. This is why, because we have an ensemble of, we can actually use an ensemble prediction versus just a single model. And then for tuning, we can potentially use this as a weighting factor. So maybe we don't tune as much on output where we're less certain. But we still have quite a bit of work to do. So we're sort of at a point where we have a starting point. We have the ensemble prediction is looking very promising, but we do have some cases where we need to kind of understand a little bit better why we're not getting as good of a prediction. And then we're going to take this and start actually using it to adjust the beamline to actually tune the quadrupoles to make sure that we can stay with the desired trajectory. So in conclusion, we've been working on using inverse models for both diagnostics and tuning. I think one of the things that the big takeaways from this work is that we've shown that inverse models can be fairly effective for diagnosing hidden parameters, or at least diagnosing parameters where you don't necessarily have them directly in the model. And that these can sometimes have unique signatures. And specifically for our application, errors in quadruple strengths, I mean, they're strongly correlated with errors in the inverse model prediction. So we see very good data on that, at least for a number of the quadrupoles. Obviously, some of them don't work quite as well, but I think we can take care of that with the use of ensemble predictions for that, which will also help with uncertainty quantification. So That's the end of my talk. Thank you very much for your time and happy to take questions.
Thank you very much, Jonathan. Do we have any questions for Jonathan? I don't see any in the slide though. All right, then if no questions, then thank you very much again, Jonathan, for your talk. And we are gonna go now to Carl Drews, who is a software engineer here at the National Center for Atmospheric Research. Welcome, Carl. And his presentation title is Marching Cubes Without Lookup Cases, Crawl the Edge Crossing Instead. Thank you.
Just going to share my screen. And that should be full screen. Is that correct?
It is.
Okay. I'm happy to be closing off the conference on improving scientific software. We're going to talk about geometry today and a lot of atmospheric chemistry. As Maggie mentioned, I am with the Atmospheric Chemistry Observations and Modeling Laboratory at NCARF. I am presenting an implementation of the Marching Cubes algorithm. This has been around for a couple decades. The code is written in Python. I am building the code here, and I intend this to be a general purpose model. The way the process works for this conference is that you give a presentation, and then I write a paper for the proceedings that is peer reviewed, and that will be published online. So this is halfway through the publication. As far as a specific example, I am running this algorithm every morning on our WRF-Chem forecasts. You see in the picture here a view of the forecast maps that I produce every day. What the intent here is to produce a three-dimensional look at what these forecasts look like. Specifically, we are interested in generating a 3D isosurface. On the map on the left-hand side here, you see a 2D contour plot, and the colors there are outlined by little lines that you can see. Those lines are the ISO lines, and they sort of travel between the grid cells of the model. So those are ISO lines at a constant contour. What we want to show is this whole thing in 3 dimensions. Now, if we look at this surface plot on the left here, I know that this is carbon monoxide, and I know this is produced by industrial processes, by traffic, by emissions from factories, things like that. And there's a big focus over Denver and a smaller focus over Fort Collins. I can see that the wind is pretty light on this day, so I'm kind of guessing there's kind of this bubble of carbon monoxide over the Denver area and a smaller bubble over Fort Collins. But I don't really know that unless I look up in 3 dimensions. This could be a long, just a bubble or a long plume that goes up and then out in some direction with the prevailing wind. And so that's why I want to look at this in 3 dimensions here and see what it looks like, see what is just above the surface. My application is atmospheric chemistry. If you look in the upper right-hand corner there, I have a plot of wildfire plumes. This is one of the fires, recent fires over Northern California. And you can see the yellow plumes are showing above where the active fire is. In this case, I noticed that we have a plume drifting out across the Pacific Ocean, blowing toward the west. And then at a higher level, we have a plume blowing toward the south. So this is not unusual that you have different wind direction and speed at different levels, but this is the kind of thing that you can look at in 3D and it's very clear what's happening right away. But in 2D, even with sections and slices, it's kind of hard to grasp what the 3D structure is. In the lower left-hand corner, I show an ozone bubble over Kansas City. Cities generate ozone by various processes involving emissions and NOx. And here we have this bubble with a long extension passing out to the south. It kind of looks like an arrow here, but this is the kind of thing we look at, this kind of this bubble, kind of a flattened bubble over a city. So these are 2 kind of things where it comes up from the surface and then goes out into the atmosphere. Stratospheric intrusions are shown in the lower right-hand corner there. These are harder. Ozone's hard. It is high, of high concentrations up in the stratosphere, but then occasionally you get these sort of lobes of ozone that come down to the surface. and they might hit the ground in some rural place like Brady, Texas. And then if somebody has a monitor there, they're wondering why on earth does the ozone suddenly get high here, the high value? It's because they have an ozone intrusion from the stratosphere down to the troposphere and down to the surface. So that's the kind of thing we're looking at as well. In addition to chemistry, this can make a isosurface of any numeric quantity that's associated with the atmosphere. For example, you could have a jet stream going from the west coast to the east coast, let's say over mostly the southern United States, and that would be a long tube of high velocity air from California to, let's say, Georgia. And if you put an airplane in that, you will save a lot of fuel. So there's a lot of interest in other quantities just beyond atmospheric chemistry, but this is the one I'm focused on. But you can make an isosurface of any numeric quantity. Marching cubes algorithm is an extension of the basic marching squares algorithm. So this is a general pattern for this presentation, is we're going to look at things in 2D and then extend them to 3 dimensions. So here's just a simple square, and we are going to consider an ISO value of 10. If one corner of the square is below 10 and the other is above 10, then we know that the contour line, the ISO value, must pass through that square by the intermediate value theorem. Pretty simple. When we extend this to marching cubes, the same property applies. If we have a value of 10 must pass between a corner which is 5 and a corner which is 15. So of the cube I've drawn there, the isosurface must pass through that cube somewhere. It doesn't matter what all the other values of the corner are. At this point, it just has to pass through there somewhere. So that's what we know by the intermediate value theorem again. Now, if we had a very high grid resolution, we'd be done. We could just plot all these cubes or plot all these squares, and that would show the ISO line. The upper left, I have shown a picture of kind of the squares marching across the page. In the lower right, I have the marching cubes marching across the surface, defining that surface. And if it were very high resolution, it would be a smooth line like the one I've shown in the middle. You're watching this display on a raster screen, I'll bet, and you have a high resolution, so that line in the middle looked pretty smooth. It's not really smooth, but if we had a high resolution, that's what we'd see here. Unfortunately, in most cases, we don't have a high enough resolution. We want to see what is happening inside the cell. So if we take a look at a cube here, in this case, we're going to look at the values of all 4 corners. We can sort of guess what is happening inside the cube or inside the square based on what's happening along those edges there. So if we have an ISO value of 10 in this case, that's between 5 and 12. I've drawn it near the bottom because that's where it crosses as calculated by linear interpolation between 5 and 12. Same kind of linear interpolation between 9 and 15. We figure that 10 point crosses closer to the 9 there. And so we have some idea of what's happening in this square here. The line follows the dark line I've drawn there across the square. This is the hard part of marching cubes. What happens in the square? What happens in the cube? There's published literature on this algorithm extending back to about 1987. And what I noticed here when I did a literature review is that 1987, 15 cases, and then 8 years later, we are up to 33 cases. And I thought to myself, it's 8 years to find and correct a problem in the algorithm. That's complicated, something funny happening here. Why does it take that long to find and correct a problem? Here is a lookup table of the cases for triangulation. In the first paper, 1987, they took a cube and sort of described all the positions that it could be, all the configurations there. In the cases you see here, the orange dot is below the isosurface and everything else is above. So these are 15 cases here. Let's look at the one on the top row, the second from the left. Only the lower left-hand corner, the front corner, is below the isosurface. Everything else is above. So the isosurface must isolate that corner there. And so you see a triangle in place there inside the cube, which isolates that. The other cases are more complicated, but these are the configurations, the 15 configurations they came up with. However, 8 years later, somebody said, Chernive said, no, there's 33. And then in another implementation, I came across the fact that there's 730 subcases. So this thing is getting kind of complicated. The number 256 comes from each of 8 corners can be in either case above or below the ISO surface. So 2 to the 8th is 256, plus a bunch of others. And the bunch of others comes from the face ambiguities. If we take a look at a idealized map of Colorado, just to make it easy to show, for you to imagine what's going on here, we have the 4 corners of Colorado here and Aspen in the middle. Great skiing in Aspen, everybody wants Aspen, okay? So what happens in the middle if the edges are defined in a symmetrical way? If we take the ISO value as 10 again, Dinosaur and Springfield are below, Julesburg and Cortez are above. So it could go either way. So this face ambiguity is the multiplier that multiplies the number of cases by 2. And this sounded to me like work. This is going to be something that's difficult to test, all these cases by symmetry and reflection. If there's one corner and you rotate it, it's a different corner, but it's the same case, and so on. How am I going to test all this? And as I was thinking over this and implementing it, I thought, how about we use a procedure instead of enumerating the cases? How about we are going to crawl around a cube instead? We're going to crawl from an edge crossing to another edge crossing. Crawl where the ISO surface crosses the edge, and then we'll go over into another face and make a decision at the ambiguity and keep crawling over the edge again until we get around to the beginning, kind of like this diagram you've seen, this graffiti of Kilroy was here. We're going to keep track of the path and accumulate 3D polygons. So that's the approach here, is to crawl these things and don't try to enumerate all the cases and flip them and rotate them into other cases. Here's a simple example of the edge crossings in our example of Colorado again. The corner at Cortez is close to the 10 mark there. And so the ISO line will go across from the west side of Colorado to the east side here and cross between the values of the corners here. And this will represent 2 edge crossings where the ISO surface crosses the edge. Each face can have 0, 2, or 4 edge crossings, because if you trace around the face, it has to go up and down and return to its place again. And so that's the number of edge crossings that are possible for any face. Looking at an example here, look at the left. In this case, it's pretty simple. We're just going to crawl around that orange dot there and generate a triangle. When we finish with that, we're done, and the triangle is stored for later rendering. If the bottom of the cube is below the ISO value and the top is above it, then we're going to crawl around the middle of the cube. It will be a rectangle. We're going to take that and record that. In the example on the right here, we have 2 isolated corners of the cube. So I'm going to generate a triangle at 1 and then a triangle at the second one. We keep crawling until all these edge crossings have been visited. Then we are done with this cube. So this is kind of difficult to sort of imagine all in your mind and keep counting edges and faces and things like that. So I got myself a little box here. And if you're going to do this, get yourself a little box and turn it over, spin it, count the faces and things like this. Get a tactile and visual aid in front of you to help you with the visualization here. So back to the face ambiguity. We come to the edge here, the north border of Colorado. Which way do we go? We have to assign the aspen to be green or yellow. And the direction we take, either to the west or the east, is going to decide that. We're going to decide it one of 2 ways. Aspen will be sort of awarded to red or to green. We can't go straight across because we have to keep the lower values on our right-hand side the way we are crossing here. So these are the 2 choices we have. And in looking at this, how should we decide this? Should we do something arbitrary? Well, I said, well, let's look at some of the, in this case here is deliberately made so everything's symmetrical, but that's usually not going to happen. How about when the values are a little different and they seem to favor one side or another? So who gets Aspen here? In this case, Julesburg and Cortez are way above the ISO value, and Dinosaur and Springfield are just a little bit below. So why should the Dinosaur Springfield axis get Aspen when it seems as if Julesburg and Cortez have some kind of better rights to it because they just have more of the border? So looking at this, I reasoned that the diagonal lines, they represent uncertainty. We want to minimize that uncertainty. So we want shorter diagonal lines in here. And so I took the strategy that we will crawl toward the edge crossing that minimizes the diagonal lines on this face. Now, another way to do this is if you imagine the state of Colorado covered with a rubber sheet, a rectangular rubber sheet, and stretched tight, what would the surface look like? Well, it would be much higher in Aspen in the middle because it will be higher than the value of 10 because Julesburg and Cortez are much higher. So this is similar to the asymptotic decider of Nielsen and Heyman, which they published as well. So it's a similar strategy going on here. Now, if we're atmospheric chemistry modelers and we really want to know what happens at Aspen, you have to run a higher resolution model. This is a reasonable interpretation of what happens inside a square or cube, and that's what we're after. We also should notice one thing, another thing at this moment is that if you decide everything, if you decide the face, resolving that ambiguity based on only information in that face, then the adjacent cubes will match up. And that's what you want when you're creating an iso surface spanning across a lot of cubes. You don't want to have a discontinuity from one cube to the next. Now, the edge crawler was going to generate a lot of triangles, but also some high order polygons. Any rectangles are certainly twisted in 3D space. 3 points defines a plane, but 4 points are probably not going to be coplanar. They're probably going to be twisted. So I made this model just to make sure I understood what was happening here. And higher order twisting can happen if you have a higher order polygon. So my approach here in triangulating this is to make a center point, a center vertex in the middle of the polygon, and then go through and rotate around that center vertex, generating triangles, which all have a point in the center there. So this is used by other authors as well. And in the end, when I run this on WorfChem output over a few hours, I generate tens of thousands of triangles, many, many triangles in the space itself and also through multiple time steps. So I do this with WorfChem, I've done it with Wacom as well, and these are encapsulated into a KMZ archive, and the file format is a Collada file. That I display with Google Earth, which is an excellent viewer and a great rendering engine. So I don't have to write all this stuff. It's there in front of me, supplied by Google Earth. The example you see here is ozone over the Los Angeles area, specifically the San Bernardino forest. We see yellow and orange inside. Those are actually yellow and red iso surfaces. I make the yellow one partly transparent so you can see what's inside. You can see the higher concentrations inside, and of course, yellow with red becomes orange. So this is the kind of thing that I generate, and it interacts with the terrain here. This is my method of rendering. I showed you a twisted rectangle made out of cardboard and duct tape a minute ago. This is what it looks like in the Google Earth renderer here. And this is ozone over Atlanta, Georgia on a certain day. And if you look on the right, you see Decatur and then maybe Sandy Springs there. The twist happens between those 2 points. And you see something which looks like my cardboard model there rendered in the Google Earth viewer here. So when we see something like that that looks like the model, then I'm happy because it sort of matches my theoretical understanding of what it should look like. So this kind of way of verifying what it looks like here. In this case, the top of the ozone bubble is being blown to the southeast by the upper winds. Now, Google Earth wants to color the surface differently depending on whether it's the inside or the outside of the bubble here. And so I have cut away the top of a ozone bubble over Denver, and we can see the different coloration there. And it's dark on the inside and lighter on the outside. There's just my convention, and that is a convenient way to do it. So the Collada file requires a normal vector for each triangle or each polygon, and I encode that into the triangles by rotating them either left-hand rule to the left or to the right, and the right-hand rule shows which way determines which way the normal vector is going to be pointing. So this is a nice way to keep all the triangles just as their vertices, and you store them in the order which determines and specifies the direction that the normal vector is pointing. There are actually 3 coordinate systems here. WorkChem latitude and longitude is kind of a Cartesian flat Earth. Everything is a height and a latitude and longitude. It is not quite flat in that it follows the terrain, and this causes some problems. In the early stages, I was looking at my northern slope of the Rocky Mountains in Colorado, and some of the panels, some of the surfaces were the wrong color. So they're pointing outside, not inside. And I was able to figure out that that was because these, instead of being cubes, they're very, very flat rectangles, because the layers of the WRF-Chem are just so thin, and because you use a higher resolution as you go higher, but this is kind of interfering with sort of the normal way of calculating inside or outside. So I also introduced normalized cube coordinates, where it's normalization based on sort of the X, Y, and Z indexes of the cube, rather than trying to do it in sort of this latitude, longitude 3 space here. So along the way, there's normalized cube coordinates because of the extreme flatness and the extreme thinness of the WRF-Chem grid. Farther along the way, if you show anything larger than just like the Front Range of Colorado, you're going to have to deal with the curvature of the Earth. Google Earth requires this by specifying a model which has a latitude and longitude, and then there's meters and X, Y, Z coordinates. So if you want something not to fly out from the Earth as the Earth bends away from it, you have to bend the coordinates down and toward the pole. Example of that. These are the spherical coordinates, the adjustment made as the last step before showing this. As I said, you in models in Google Earth have a center point, and then I use the entire span of the WRF-Chem model as my 3D model. So I just have one model to deal with. And let's say I'm standing on the border between Colorado and New Mexico on State Line Peak, which is about between the east and the west border of Colorado. I extend out my left arm straight to the west, facing north, extend out my right arm to the east. If my left arm was very long and went perfectly straight, I would end up not over 4 corners. I'd end up somewhere else. I'd end up above it and south. As it turns out, if you do a rotational matrix here, 4 corners has to be 5.7 kilometers north of straight to the left, and it has to be 7.6 kilometers down. And I've shown that here by drawing a giant wall over the southern border of Colorado. Otherwise, the wall flies away from the Earth's surface. So this is another adjustment you have to make. And this is the third coordinate system. So to review and to wrap it up, what is the purpose for this? Why are we looking at 3D when we have these nice 2D plots to look at? It's difficult to understand the structure of the atmosphere using just 2D plots, sections, slices alone. This I have shown here is a plot at NASA Langley of a LiDAR at Hampton, Virginia, which points straight up and shows you the ozone above you. Gives you a profile of the ozone, very nice. And this is a time, the x-axis here is time. So fascinating, but what happened here? Did we get a bunch of ozone, a bubble that just suddenly came down at time 12 and then disappeared? Or maybe it's moving across the LiDAR from east to west, north to south. And what is this long tail that's coming out on the right here? Well, you could figure out these things by a bunch of different time slices at different places and horizontal slices and vertical slices, and those will certainly be more accurate. But in order to find out what is happening in 3D here and in 4D, it's really useful to be able to show an ISO surface, a view that you can rotate over and move and see what's happening before you go in and make a surface at the right, a section plot at the right place. Lastly, I'm going to show a 3D animation here. This is one of the Fire XAQ flights we did over the Williams Flats fire during that field campaign. And what we were trying to do is fly around the airplane and go through some pyrocumulus clouds, which also have definitely a time element to them as well. And my friend and colleague Becky Hornbrook is on this flight. So here we go. The DC-8 is a big airplane, and for every morning, for about 3 hours, it's a flight planning meeting. There's about 40 people in the meeting. And if you do the math, that's a lot of money with the airplane and the people. So there's a lot of incentive here and a lot of financial incentive to fly at the right place on the right time. And so putting effort into getting exactly this right and seeing exactly where things are in space and flying through them is definitely worth the effort here. Thank you for your attention. I'll be happy to take any questions.
Thank you very much, Carl. That was very interesting. Teja here, she put, I really appreciated 3D models you made to show us. And I concur. It was very cool to see.
Good. That video is on the ACOM YouTube channel. And I have tried to show a bunch of things so you get the feel for what's happening and the airplane flying through. Mm-hmm.
Absolutely. Any more questions? Any other questions? All right. So, well, if there are no questions, then thank you very much, Carl, again, for a very interesting presentation. Thank you to all the speakers that presented today, and as well as before lunch and after lunch. And I guess this concludes our Improving Scientific Software Conference of 2022. Yeah. Thank you so much. Wait, I'm not showing my video. I want to show my video because I also want to clap. At the end, so I would like to thank the moderators and the speakers and Teja and Brett and Davide and the organizing committee. And of course, as well as the sponsor, Fluid Numerics, for making this workshop possible. We started several months back, and it's so nice to see it come to fruition and have so many good presentations. And thank you all for participating, because you are the ones that make this so interesting and possible. We hope you enjoy it. We would like to let you know that the proceedings for the conference will be available in early July. So please keep an eye out for all the emails. I'm sure there are going to be emails about it. I don't know if there's anything else, Teja or Brett, that you guys want to say. Okay, so yeah, so Teja is mentioning she's going to be sending a survey. Please take it. Yes, we will definitely appreciate it, because when we were organizing this workshop, we were definitely looking at the surveys from the last one. So please do. And let's see, anything else?
No, that's all for me. I just want to thank everybody as well. So, and thank you, Maggie, for moderating today.
Sure. Eric is asking if the videos. Yeah, so I think the videos, Eric, that will be in July with the proceedings.
Oh, I'll put the videos out next week, actually, or probably in the next 2 weeks. I just have to get them all put up on YouTube. And then the proceedings, like the papers, I'll send an email when those are available after we review them, and that'll be in July.
All right. Well, then, thank you. Thank you very much. You guys have a wonderful Friday. If you're in Colorado, it finally stopped blowing the wind. So it's beautiful out there. So, but thank you very much, everybody. And you guys have a wonderful day.
Thank you, Teja.
Everybody, thanks, Carl.
Bye-bye.